Hello there and welcome to our channel, where curiosity gets comfortable and science takes the long, scenic road toward rest. Tonight, we are stepping far beyond the familiar outlines of our modern world, past today's continents and oceans, past the shapes we recognize on maps, and into a time when the planet itself wore a very different face. Our gentle journey will carry us back hundreds of millions of years, to an era when nearly all of Earth's land was gathered together into a single immense supercontinent known as Rodinia. Before we begin drifting through that ancient world, let me ask you something simple and quietly personal. Where are you listening from right now? Is it late evening with the lights dimmed low, or early morning, with the sky just beginning to soften? And if you happen to glance at a clock, what time does it say in your little corner of the planet? It feels fitting, doesn't it, to think about time while preparing to travel so far beyond our own. If you find this slow exploration calming or interesting, I'd be grateful if you gave the video a like or perhaps subscribed. It helps this small, quiet space reach others who might enjoy a peaceful pause at the end of a long day. Now settle in. Let your thoughts ease back and allow the world around you to fade just a little. We're about to step into a version of Earth that feels almost impossible. A planet shaped by forces so slow and powerful that they make our own lifetimes seem like brief flickers of light. To understand what Earth was like during the time of Rodinia, it helps to begin with a simple image. Imagine looking down at the planet from far above. Not as a blue marble with scattered continents, but as a single sprawling land mass wrapped by one vast, uninterrupted ocean. No Atlantic, no Pacific, no Indian Ocean dividing familiar shores. Instead, land stretches on and on, curving over the horizon in every direction, stitched together by ancient mountain belts and broad, empty plains. Rodinia formed more than 1 billion years ago during a chapter of Earth's history known as the Proterozoic Eon. This was a world long before dinosaurs, long before trees, long before anything that would look like a fish or a bird or a mammal. Life existed certainly, but it was quiet, subtle, and mostly invisible to the naked eye. The planet itself, however, was anything but still. Deep inside, heat from Earth's interior slowly churned the mantle, moving colossal slabs of crust across the surface like pieces of a puzzle that took hundreds of millions of years to rearrange. Those moving pieces eventually came together to form Rodinia. The name itself comes from a Russian word meaning to give birth or to beget, because this supercontinent is thought to have given rise to many of the land masses we recognize today. But during its time, Rodinia was less a birthplace and more a gathering. A long, slow embrace of ancient continents drawn together by the relentless pull of tectonic forces. If you had stood on Rodinia's surface, though, you would not have seen continents drifting or plates grinding past each other. The ground beneath your feet would have felt solid and unmoving just as it does now. The changes happened so slowly that no living thing could ever notice them. Mountains rose over millions of years, not in dramatic bursts, but in quiet, steady motion, like a breath drawn so slowly you barely realize it's happening. The sky above Rodinia would have looked familiar in some ways and strange in others. The sun would still rise and set, tracing its arc across the sky, but its light would fall on a world with no grass, no forests, and no animals to cast moving shadows. The land would have been largely bare rock, dust, and perhaps thin films of microbial life clinging to damp surfaces near water. Colors would be muted, dominated by the browns and grays of stone, the dark blues of distant seas, and the pale glow of clouds drifting overhead. At this point in Earth's story, the atmosphere was still evolving. Oxygen existed, but not in the rich abundance we enjoy today. The air may have felt thinner, sharper, and less forgiving to anything that breathed deeply. Complex life, as we know it, had not yet learned how to make use of that oxygen in the way animals would much later. Instead, most living things were content, or perhaps simply adapted to life at a microscopic scale. The oceans that wrapped around Rodinia formed a single global body of water, often referred to by scientists as the Morovia Ocean. It surrounded the supercontinent like a vast, unbroken moat, stretching from one horizon to the other. Waves rolled in slow, steady rhythms against long, empty coastlines. There were no shells scattered along the shore, no birds calling overhead, no plants rooted in the sand. The soundscape of this ancient world would have been simple and sparse. Wind across stone, water against rock, and perhaps the distant rumble of volcanic activity far away. Rodinia itself was not a smooth or uniform place. It was stitched together from older continental fragments, each with its own deep history. Where these pieces collided, massive mountain ranges rose, some of them likely as tall or taller than anything we see today. Over time, erosion wore them down, grain by grain, carrying their remains into the surrounding seas. Rivers flowed across the land, though their courses would have been different from anything we know now, shaped by unfamiliar slopes and distant coastlines. Those rivers carried minerals and sediments into the ocean, feeding vast microbial communities that thrived in shallow coastal waters. These tiny organisms, often forming layered structures known as stromatolites, were among the most successful life forms on the planet at the time. They quietly captured sunlight, processed chemicals, and left behind subtle signatures in the rocks that scientists still study today. If you were to walk across Rodinia, you might travel for weeks or months without seeing anything that moved in a way you could easily recognize as light. No insects buzzed through the air. No animals darted across the ground. Instead, life hid in thin films on rocks, in mats beneath shallow water, and in microscopic worlds far too small for human eyes. Yet despite this apparent emptiness, the planet was alive in its own way, pulsing with slow chemical cycles and the steady exchange of gases between land, sea, and sky. The climate of Rodinia was another piece of this quiet, unfamiliar puzzle. Because the supercontinent gathered so much land into one place, it affected how heat and moisture moved around the globe. Large interiors of the continent may have been dry and harsh, far from the moderating influence of the surrounding ocean. Along the coasts, conditions could be milder with more frequent rainfall and shifting clouds. At times, Earth during Rodinia's age may have experienced extreme cold episodes that scientists now refer to as snowball Earth events. During these periods, ice may have spread across much of the planet, possibly even reaching the equator. Imagine standing on a shoreline and seeing ice stretching out across the sea as far as you can see, reflecting sunlight back into the sky, cooling the planet even further in a powerful feedback loop. Whether Rodinia was fully frozen or only partially iced over during these times is still a topic of study and discussion. What is clear is that the climate swung between long periods of relative warmth and deep global cold, creating challenges and opportunities for the simple life that existed then. Deep beneath all of this, far below the crust you might stand on, Earth's interior continued its slow, restless motion. Hot material rose from the mantle, cooled, and sank again, dragging the overlying plates along for the ride. This invisible engine was already preparing Rodinia's eventual fate, even as the supercontinent sat united on the surface. Forces were building that would one day pull it apart. But for now, in this moment of our story, Rodinia remained whole. It was a world defined by scale, by slowness, and by a kind of quiet persistence that is hard to imagine from the pace of modern life. A single day meant little in the grand scheme of things. Even 1,000 years was barely a blink. Change came measured in millions of years, in the patient rise and fall of land, in the gradual shifting of climates, and in the steady evolution of life at a microscopic level. It can be strangely calming to think about a world like this, a planet not yet shaped by cities, roads, or even forests. A place where the loudest sounds might have been wind across stone or waves breaking against empty shores. Time moved certainly, but it did so without deadlines, without calendars, and without anyone counting the hours. As you rest and listen, perhaps take a slow breath and imagine that ancient horizon. Picture a low sun casting long shadows across a bare rocky plain. In the distance, mountains rise, worn and ancient, even in their own time. The sky stretches wide above, and beyond that, the stars wait just as they always have. Long before the outlines of today's continents took shape, before the oceans we know carved their familiar paths between distant shores, the planet held its land in a single vast gathering. If you could drift above Earth during this time and look down through the clouds, you would not see a patchwork of separate worlds. Instead, you would see one immense land mass stretching across the globe. A continuous sweep of stone and soil that curved with the planet itself. This was Rodinia, a supercontinent formed through patient, relentless motion, guided not by sudden drama, but by the quiet persistence of deep forces beneath the surface. The idea that all lands were once joined might feel almost like a story passed down through imagination. But the reality is written into the rocks beneath our feet. Every continent today carries subtle clues, fragments of an ancient puzzle that once fit together in a very different arrangement. To meet Rodinia is not just to picture a distant place in time, but to follow a trail of evidence scattered across mountains, deserts, and coastlines all around the modern world. The story begins far below the surface in a region we can never directly visit, yet one that shapes everything above it. The mantle, a thick layer of slowly moving rock beneath Earth's crust, behaves in a way that feels almost contradictory. It is solid, yet over immense spans of time it flows. Heat from the planet's interior rises upward in broad currents, cools near the surface, and sinks again. This slow circulation acts like a conveyor belt for the crust, carrying massive slabs of rock known as tectonic plates across the surface of the globe. These plates do not glide smoothly. They grind, collide, and pull apart, sometimes locking together for millions of years, sometimes slipping past one another in brief, violent moments. Over time, these interactions reshape the planet's face. Oceans open and close. Mountains rise and erode. Continents wander across latitudes, drifting from equatorial warmth to polar chill and back again. Rodinia was born from one of these long cycles of assembly. Before it existed, Earth's land was already divided into several older continental blocks, each with its own deep history. These fragments, sometimes called cratons, were the ancient cores of continents, stable and thick, carrying within them records of even earlier worlds. Over hundreds of millions of years, tectonic motion slowly nudged these blocks closer together. Where two pieces of crust met, neither wanted to sink easily. Instead, they crumpled, folded, and thickened, pushing up vast mountain ranges. These were not the sharp, jagged peaks we often imagine, but broad, towering systems that stretched for thousands of kilom. Over time, wind, water, and ice wore them down, carrying their remains away grain by grain. Yet their roots stayed behind, locked into the deep structure of the growing supercontinent. As more fragments joined, Rodinia took on a rough shape, though not one as neatly defined as a modern map. Its outline shifted as plates continued to press together, and its interior became a complex mosaic of welded terrains. Some regions were once coastal margins, now stranded far inland. Others were the crushed remains of ancient ocean basins, trapped between colliding land masses and transformed into bands of dense, altered rock. If you were to stand somewhere near the center of Rodinia, you might find yourself farther from the ocean than any place on Earth today. The air could feel dry, the landscape wide and open with long horizons broken only by distant ridges or low, worn hills. Rivers would still flow, carving paths across the land, but their journeys to the sea could take immense distances, crossing environments that shifted slowly from upland to lowland, from rocky terrain to broad, sediment-filled plains. The coastlines of Rodinia, by contrast, would have been places of constant change. Tides rose and fell against bare rock and shallow shelves. Waves carried sediments eroded from the interior, and spread them along the margins of the supercontinent. In these shallow waters, life found some of its most favorable conditions. Microbial communities formed layered structures, building up over time in slow, steady growth. These living mats trapped particles, cemented them together, and left behind distinct patterns in the rocks that still persist today as some of the oldest visible traces of life on Earth. Understanding where Rodinia sat on the globe is another piece of the puzzle that scientists continue to refine. Evidence suggests that it may have been positioned mostly in the tropics for part of its existence, allowing intense sunlight to heat its surface and drive strong weathering. This would have helped pull carbon dioxide out of the atmosphere as minerals reacted with rainwater, potentially influencing the planet's climate in profound ways. Other clues hint that parts of Rodinia may have drifted toward higher latitudes at different times, exposing them to cooler conditions and possibly contributing to the great ice ages that punctuated this era. The movement of a supercontinent across the globe does more than change what the land experiences. It reshapes how oceans circulate, how winds blow, and how heat is distributed between equator and poles. The ocean surrounding Rodinia was not just a passive backdrop. It played an active role in the planet's systems. Currents carried warm water away from equatorial regions and returned cooler water from higher latitudes. The chemistry of these waters influenced the kinds of life that could thrive, the minerals that settled onto the seafloor, and the gases exchanged with the atmosphere above. Deep beneath the waves, the seafloor itself was in motion. Along hidden ridges, new crust formed as molten rock rose and cooled. Elsewhere, old crust sank back into the mantle at subduction zones, disappearing beneath the edges of the supercontinent. These processes helped regulate the planet's internal heat and contributed to the slow reshaping of Rodinia's margins. From a human perspective, it can be difficult to grasp just how gradual all of this was. A single mountain range might take tens of millions of years to rise, only to be worn down again over a similar span. An ocean basin could open, widen, and close over a few 100 million years, leaving behind only a faint line of altered rock to mark where water once flowed. To meet Rodinia, then, is to meet time on a scale that stretches the imagination. It is a reminder that the ground beneath us is not a fixed stage, but a moving part of a long, ongoing process. The continents we recognize today are temporary arrangements, snapshots in a sequence that has been unfolding for billions of years. Scientists piece together Rodinia's form and history using a variety of tools, each offering a different kind of insight. One of the most important is paleomagnetism, the study of ancient magnetic signals locked into rocks. When volcanic or sedimentary rocks form, minerals within them align with Earth's magnetic field. Because that field changes over time and space, these tiny alignments can reveal the latitude at which a rock formed. By comparing such signals from different continents, researchers can estimate how those land masses were positioned relative to one another long ago. Another line of evidence comes from matching geological features across modern continents. Mountain belts of similar age and structure can sometimes be traced from one land mass to another, suggesting they were once part of the same continuous range. Rock types, mineral deposits, and even ancient sediment layers can line up like matching edges of a torn photograph. For example, parts of what is now eastern North America show striking similarities to regions in Western Africa and parts of South America, hinting at connections that date back to supercontinents like Rodinia and its successors. These connections are not always obvious on the surface, but deep within the crust, the signatures remain. Fossils, though rare in rocks this old, also play a role. Certain types of ancient life appear in sediments that are now separated by oceans, suggesting that those environments were once connected, or at least close enough for similar organisms to thrive in comparable conditions. As these pieces come together, a picture emerges of Rodinia as a dynamic, evolving world, not a static block of stone. Its interior shifted, its edges changed, and its relationship with the surrounding ocean and atmosphere influenced the entire planet. Yet for all this motion, there was a sense of unity in Rodinia's existence. All of Earth's major land masses shared a common setting, a single stage on which the slow drama of geological change played out. Weather patterns, ocean currents, and even the global climate were shaped by this unusual configuration. The presence of such a large, continuous land mass likely affected rainfall patterns. Moist air traveling inland from the coast would lose much of its water along the way, leaving central regions drier. This could create vast interior areas where erosion happened differently, where rivers carried less water, but still transported fine sediments over great distances. Along the coasts, by contrast, more active weather systems could bring stronger winds and heavier rains, shaping cliffs, deltas, and shallow seas. These areas would have been hubs of chemical exchange between land and ocean, places where minerals washed into the water and influenced its composition. The atmosphere above Rodinia was part of this system as well. Volcanic activity released gases from Earth's interior, including carbon dioxide, which helped regulate temperature through the greenhouse effect. At the same time, weathering of rocks on the surface removed carbon dioxide from the air, locking it into minerals that eventually settled on the seafloor. This balance between release and removal helped stabilize the planet's climate over long periods, even as conditions shifted dramatically from warmth to deep cold and back again. In this way, Rodinia was not just a collection of rocks, but a central player in Earth's evolving systems. It can be quietly humbling to think that every continent we know today once shared a common past in this ancient gathering. The land beneath your feet, wherever you are, was once part of a much larger whole. It traveled across the globe, collided with distant neighbors, and eventually drifted apart again, carrying with it a memory of that long union. As Rodinia persisted, it also set the stage for what would come next. The same forces that brought the continents together continued to work, slowly building tension within the crust. Heat accumulated beneath certain regions. Cracks formed, at first too small to notice, then gradually widening. Magma rose into these fractures, cooling and hardening, pushing the surrounding rock aside. Over time, these rifts stretched and thinned the crust, making it easier for the land to begin pulling apart. Rivers found new paths along these low points. The surface subtly reshaped itself in response. This process would eventually lead to Rodinia's breakup, a transformation that would give rise to new oceans and set the continents on journeys toward the positions we recognize today. But in this moment of our exploration, that future remains just out of view, a gentle suggestion rather than a conclusion. For now, it is enough to sit with the image of a unified Earth, a planet holding its lands together in a single immense form. A world where the distances were vast, the changes were slow, and the signs of life were quiet and small yet persistent. If you are somehow able to stand on the surface of Earth during the age of Rodinia and lift your eyes toward the sky, the first thing you might notice is not what is there, but what feels subtly different about the air itself. The sky would still stretch wide above you. Clouds would still drift and gather, and the sun would still rise and fall in a familiar rhythm. Yet the atmosphere surrounding you would belong to a planet at a very different stage of its long story, shaped by chemical balances and biological processes that were still finding their way toward what we now take for granted. The deep Proterozoic was a time when Earth's atmosphere had already passed through one of its most dramatic transformations, but had not yet settled into the stable oxygen-rich mixture we breathe today. Hundreds of millions of years earlier, microscopic organisms had begun releasing oxygen as a byproduct of photosynthesis, slowly altering the composition of the air in what scientists call the Great Oxidation Event. By the time Rodinia formed, this process had been underway for a long while, but its effects were still unfolding, and the sky above the supercontinent reflected a world in transition. Oxygen levels during this period were likely much lower than modern values, perhaps only a fraction of what fills the air today. For humans, such an atmosphere would feel thin and difficult to breathe, but for the life forms of the time, it was simply normal. Most organisms did not rely on oxygen in the way animals do. Instead, they used a variety of chemical pathways to gain energy. Many of them well suited to low oxygen or even oxygen-free environments. This difference in air composition would have influenced more than just breathing. It shaped how the sky looked, how sunlight filtered down to the surface, and how weather systems developed across the vast land mass of Rodinia. The presence or absence of certain gases affects how light scatters in the atmosphere, and that in turn changes the color and brightness of the sky. Today, our blue sky is the result of sunlight interacting with nitrogen and oxygen molecules, scattering shorter blue wavelengths more efficiently than longer red ones. In the Proterozoic, with different proportions of gases and potentially more haze forming particles in the air, the sky may have taken on a different tone. Some scientists suggest it could have appeared paler, perhaps tinged with a faint haze that softened the sun's glare and muted the sharpness of shadows on the ground. This haze may have come from a combination of volcanic gases, methane produced by early life, and fine particles lifted into the air by wind sweeping across bare rocky landscapes. Without forests or grassy plains to anchor the soil, large areas of land could have been more easily eroded, sending dust into the atmosphere where it could linger for long periods. The sun itself, though following the same daily path across the sky, was slightly different in its output. Billions of years ago, the sun was dimmer than it is today, producing less energy overall. This faint young sun paradox presents an interesting question. If the sun was weaker, why was the planet not permanently frozen? Part of the answer lies in the atmosphere's ability to trap heat. Greenhouse gases such as carbon dioxide and methane were likely present in higher concentrations than they are now. These gases absorb and remit infrared radiation, helping to keep the planet warm despite the sun's lower output. In this way, the ski over Rodinia played a direct role in maintaining temperatures that allowed liquid water to exist across much of the planet. Carbon dioxide entered the atmosphere through volcanic activity, as molten rock rising from the mantle released trapped gases into the air. Over time, this carbon dioxide was gradually removed through weathering processes. Rainwater absorbed the gas, forming a weak acid that reacted with exposed rock on the surface. The products of these reactions were carried by rivers into the ocean, where they eventually became part of sedimentary layers on the seafloor. This slow exchange between air, land, and sea formed a long-term feedback system. When carbon dioxide levels rose, the planet warmed, increasing rainfall and weathering, which in turn pulled more carbon dioxide out of the atmosphere. When levels fell, the planet cooled, slowing these processes and allowing volcanic emissions to build the gas back up again. Over millions of years, this cycle helped regulate Earth's climate, even as conditions swung between extremes. Methane, another powerful greenhouse gas, was likely abundant in the Proterozoic atmosphere. Many early microbes produced methane as part of their metabolic processes, especially in low oxygen environments such as shallow seas, wetlands, and sediments. In the absence of high oxygen levels, methane could persist in the atmosphere longer than it does today, contributing significantly to warming. The interaction between methane and oxygen also played a role in shaping the sky's appearance. When these gases reacted, they could form complex organic molecules that created a kind of atmospheric haze, similar to what we see today on Saturn's moon Titan. Such a haze would scatter sunlight, potentially giving the sky a softer, more diffuse quality and reducing the amount of direct solar radiation reaching the surface. Clouds during this time would have formed in much the same way they do now as warm, moist air rose, cooled, and condensed into droplets or ice crystals. However, the distribution and behavior of clouds were influenced by the unusual layout of the planet's land and sea. With one vast supercontinent and a single surrounding ocean, atmospheric circulation patterns likely differed from the modern system of multiple continents and interconnected seas. Large land masses heat and cool more quickly than oceans. During the day, the interior of Rodinia would warm under the sun, causing air to rise and draw in cooler, moist air from the surrounding ocean. At night, the land would cool more rapidly, revering these flows. This daily breathing of the atmosphere could drive strong winds across the continent's margins, shaping weather patterns and influencing where clouds formed and where rain fell. Seasonal changes added another layer of complexity. Depending on Rodinia's position on the globe, different parts of the supercontinent experienced shifts in sunlight over the course of the year. Regions closer to the equator received more consistent solar energy, while those farther north or south saw greater variation between brighter summers and darker winters. These variations affected temperature, which in turn influenced atmospheric pressure and wind patterns over long periods. These winds sculpted the landscape, moving sand and dust across open plains, carving subtle features into exposed rock and contributing to the spread of fine particles into the air. Storms likely existed as well, though their nature remains a subject of study. Thunderstorms require strong temperature contrasts and sufficient moisture, conditions that could have been present along Rodinia's coastal regions and in certain inland areas where warm air met cooler flows. Lightning from these storms may have played a role in chemical reactions in the atmosphere, helping to fix nitrogen into forms that could be used by living organisms. Nitrogen itself was probably the most abundant gas in the Proterozoic atmosphere, just as it is today. It is largely inert, meaning it does not easily react with other substances, and so it tends to accumulate over time. This stable background gas provided the bulk of the atmosphere's mass, setting the stage for the more active players like oxygen, carbon dioxide, and methane to influence climate and chemistry. One of the most important consequences of rising oxygen levels was the gradual formation of an ozone layer high in the atmosphere. Ozone, a form of oxygen made of 3 atoms instead of 2, absorbs much of the sun's harmful ultraviolet radiation. Before this layer became well established, UV light would have reached the surface in greater intensity, making the land a harsh place for life. By the time of Rodinia, the ozone layer was likely developing, offering increasing protection. This change may have helped open the door for more complex life forms to explore shallow waters, and eventually the edges of the land itself. The sky above then was not just a passive dome, but an active shield, shaping where life could survive and how it could evolve. The interaction between the atmosphere and the ocean was another defining feature of this era. Gases constantly move between air and water, dissolving into the sea or escaping back into the sky. Oxygen produced by photosynthetic organisms in the ocean slowly accumulated in the air, while carbon dioxide from the atmosphere dissolved into the water, influencing its chemistry. These exchanges affected the formation of certain types of rocks that we still find today. For example, the presence of oxygen allowed iron dissolved in ancient seas to oxidize and precipitate out, forming layers of iron-rich sediments known as banded iron formations. While many of these formed earlier in Earth's history, similar processes continued to shape the composition of the ocean and the rocks laid down during the Proterozoic. Volcanic eruptions punctuated the quiet rhythm of atmospheric change. When volcanoes erupted, they injected ash and gases high into the sky. Ash clouds could spread over large areas, blocking sunlight and cooling the surface temporarily. Gases like sulfur dioxide could react with water vapor to form tiny droplets of sulfuric acid, which reflected sunlight and influenced climate on short time scales. These events were brief compared to the slow march of geological time, but they added variation to the planet's climate and left chemical fingerprints in the layers of rock that formed during and after each eruption. Over millions of years, the accumulation of such layers created a detailed archive of atmospheric conditions that scientists now read like pages in a very old book. From the ground, a person standing on Rodinia might have experienced the atmosphere as both familiar and alien. The wind would still brush against the skin. Clouds would still gather on the horizon. Rain would still fall, carving channels in the land and filling shallow basins. Yet the air itself, with its different mix of gases and particles, would carry a subtle strangeness, a reminder that this was a world still finding its balance. Sound would travel differently in air of slightly different density. Smells, if any, were present in a landscape largely devoid of plants and animals, might carry farther or fade more quickly. Breathing would feel like a gentle effort, not an automatic ease. The sky colors might shift at dawn and dusk in ways that feel just a little off from what we're used to seeing. At night, the stars would shine with particular clarity in regions far from volcanic haze or coastal clouds. With no artificial light and no forest to block the view, the night sky over Rodinia's interior could be a wide, open canvas of starlight. The Milky Way would stretch overhead, its pale band cutting across the darkness, unchanged by the passage of continents below. The atmosphere also carried the slow rhythm of the planet's rotation. Days were slightly shorter then than they are now. Earth's spin has been gradually slowing over billions of years due to the gravitational interaction with the moon. During the Proterozoic, a day may have been a few hours shorter, though still long enough to follow a familiar pattern of light and dark. This subtle difference influenced how the atmosphere moved. Faster rotation can affect the strength and structure of wind patterns, shaping the way air circulates from equator to poles and back again. These patterns in turn influenced where clouds formed, where rain fell, and how heat was distributed across the supercontinent. As the sky over Rodinia continued to evolve, it played a quiet but crucial role in preparing the planet for what would come later. The gradual increase in oxygen, the development of the ozone layer, and the stabilization of climate through long-term feedbacks all set the stage for the rise of more complex life in the eras that followed. Yet during this time, that future remained only a possibility, written into chemical gradients and slow biological changes that no one could observe or anticipate. The atmosphere was both a record of what had already happened and a promise of what might one day be. It is easy to think of the sky as something distant and untouchable. But during Rodinia's age, as now, it was intimately connected to the ground below. Every gust of wind, every falling drop of rain, every shifting cloud was part of a continuous exchange between Earth's surface and the space above it. Imagine standing on a wide, empty plain under that ancient sky. The air moves gently, carrying fine dust across the land. Clouds gather slowly in the distance. The sun hangs low, its light softened by a faint haze. There is a sense of space and time stretching outward, of a planet quietly working through its own long story. If you were to step away from the land of Rodinia and move outward toward the edge of the supercontinent, the ground beneath your feet would eventually begin to change. Solid rock would give way to softer sediments worn smooth by countless waves and slow-moving water. The air would carry a different scent, faint and mineral, shaped by salt and moisture rather than dust and stone. Ahead of you, stretching far beyond any visible horizon, would be the vast global ocean that wrapped around the world like a single unbroken band. This ocean, often called Morovia by scientists, was not divided into named basins or bordered by familiar coastlines. There was no Atlantic opening between distant continents, no Pacific separating east from west. Instead, water surrounded Rodinia on nearly every side, forming one immense body that connected all shores into a continuous planetary system. To stand at its edge would be to look out over a surface that might continue uninterrupted for tens of thousands of kilom. The sheer scale of this sea shaped everything about Earth's climate, chemistry and life during this time. Oceans are not just collections of water. They are moving breathing systems that store heat, carry nutrients, and exchange gases with the sky above. In the age of Rodinia, with so much water connected into a single global system, these processes took on a different rhythm than they do today. Surface currents would have traced wide, sweeping paths around the supercontinent, driven by wind patterns and the slow rotation of the planet. Warm water near equatorial regions would drift toward higher latitudes, releasing heat into the air before cooling and sinking. Colder, denser water would then flow back toward the equator at depth, completing a slow, global circulation loop. This movement helped distribute heat across the planet, softening temperature extremes and linking distant parts of the ocean into one connected system. Yet the presence of a massive continuous landmass altered these flows in subtle ways. Modern ocean currents often weave between continents, funneled through narrow straits or guided by the shape of coastlines. In Rodinia's time, those pathways were fewer. Water had to move around the edges of a single sprawling barrier, creating broad looping patterns that could persist for millions of years. These currents influenced where nutrients collected and where life could thrive. Along certain stretches of coastline, deeper waters rich in dissolved minerals and chemicals might rise toward the surface, a process known as upwelling. In these regions, microbial communities could flourish, feeding on the steady supply of nutrients and forming dense layered mats in shallow seas. Farther from shore in the open ocean, conditions were likely quieter and more uniform. Light faded quickly with depth, and much of the water column would have been dim and cold, especially in regions far from the sun-warmed surface. Life still existed there, but it was sparse, adapted to low energy conditions and slow rates of change. The chemistry of Rodinia's oceans reflected the atmosphere above and the rocks below. Carbon dioxide from the air dissolved into the water, forming carbonic acid that reacted with minerals washed in from the land. This process influenced the ocean's acidity, which in turn affected how easily certain minerals could form and settle onto the seafloor. Oxygen slowly increasing in the atmosphere also made its way into the sea. In surface waters, where sunlight reached and photosynthetic organisms lived, oxygen levels could be relatively higher. In deeper layers, especially where circulation was slow, oxygen might be scarce or absent altogether. These low oxygen zones created distinct environments, shaping which kinds of microbes could survive and how chemical reactions played out in the water. One of the most striking features of ancient oceans like Morovia was the way they recorded their own history. Over time, particles settled out of the water and accumulated on the seafloor. Some were tiny grains of sand or clay carried in by rivers. Others were the remains of microscopic organisms, shells or mineral coatings that formed around living cells. Still others were chemical precipitates, minerals that crystallized directly from seawater under the right conditions. Layer by layer, these materials built up, forming sedimentary rocks that captured a snapshot of the ocean's state at the moment they were laid down. Changes in temperature, chemistry, and biological activity left subtle marks in the composition of these layers. Today, scientists drill into these ancient deposits and read them like a long, slow-moving record of Earth's past. Volcanic activity added another dimension to the ocean's character. Along hidden ridges and subduction zones, molten rock rose from the mantle and met the cold water above. In these places, known as hydrothermal vents, superheated mineral-rich fluids poured into the sea carrying dissolved metals and chemicals. These vents created localized environments that were warm, dark, and chemically distinct from the surrounding waters. Even in the deep Proterozoic, they likely supported unique communities of microbes that drew energy not from sunlight, but from chemical reactions involving sulfur, iron, and other elements. This form of life, known as chemosynthesis, offered an alternative path for survival in a world where light-based ecosystems were still limited. The presence of such environments hints at the diversity of conditions within Rodinia's oceans. Even in the absence of complex plants and animals, from sunlit shallows to dark mineral-rich depths, the sea offered a range of habitats that encouraged experimentation in life's earliest forms. The coastlines of the supercontinent were places of constant motion. Tides driven by the gravitational pull of the moon rose and fell across wide, shallow shelves. These shelves extended far out from the land in many regions, creating broad zones where water depth changed gently over long distances. In these areas, waves and currents spread sediments across the seafloor, forming layered deposits that could stretch for hundreds of kilometers. Microbial mats grew on these surfaces, trapping particles and stabilizing the sediment. Over time, these mats were buried and preserved, leaving behind distinctive structures that scientists now recognize as some of the oldest visible signs of life. Storms could dramatically reshape these coastal environments. Strong winds pushed waves inland, eroding shorelines and redistributing sand and mud. Floods from rivers added fresh layers of sediment, altering the shape of deltas and shallow basins. Each event left its mark, contributing to the complex patchwork of deposits that built up along Rodinia's edges. Beyond the shallows, the ocean floor dropped away into deeper basins. Here, fine particles settled slowly through the water, forming thin, even layers over long periods. The lack of strong currents in these depths meant that the seafloor could remain relatively undisturbed for thousands of years at a time, allowing delicate chemical and biological signatures to be preserved. The temperature of the ocean varied with depth and location. Near the surface, especially in equatorial regions, water could be relatively warm, warmed by the sun and mixed by wind-driven waves. At greater depths, temperatures fell and the water became colder and denser. This stratification influenced how easily gases and nutrients could move between layers, shaping the overall behavior of the ocean system. During periods when Earth's climate cooled dramatically, ice may have spread across large portions of the ocean's surface. In extreme scenarios, ice could have extended far from the poles, possibly reaching low latitudes. This would have reflected sunlight back into space, reinforcing the cooling and altering the exchange of gases between ocean and atmosphere. Even under ice, however, the ocean did not stop moving. Beneath the frozen surface, currents continued to flow and life persisted in sheltered environments where liquid water remained. These hidden seas carried on their slow circulation, maintaining chemical connections between distant regions of the planet even during the coldest episodes. The relationship between the ocean and the land was a two-way exchange. Rivers carried dissolved minerals from the weathering of Rodinia's surface into the sea. These inputs influenced the ocean's chemistry, providing elements that organisms use to build their structures or carry out metabolic processes. In return, the ocean shaped the land. Waves eroded coastlines, carving cliffs and smoothing rocky outcrops. Salt spray and moisture altered the chemistry of exposed surfaces, contributing to the slow breakdown of minerals. Over long periods, these interactions helped define the shape of the supercontinent's margins. The sea also played a role in regulating atmospheric composition. Carbon dioxide dissolved into surface waters, where it could be used by photosynthetic organisms or incorporated into mineral forms. Oxygen produced in the ocean's sunlit layers escaped into the air, slowly increasing atmospheric levels. This exchange created a feedback loop between ocean and sky, linking biological activity in the water to conditions experienced on land. The pace of this process was slow, measured in millions of years, but its impact was profound, gradually transforming the planet's surface environment. From a human point of view, it can be difficult to imagine an ocean without the familiar signs of modern marine life. No fish darting through the water, no whales breaking the surface, no coral reefs building colorful structures beneath the waves. Instead, the Sea of Rodinia's time was a quieter place, dominated by microscopic life and simple, soft-bodied organisms. Yet in its own way, it was just as dynamic. Chemical gradients shifted. Populations of microbes rose and fell, and layers of sediment recorded each change in careful detail. The ocean was not waiting for complexity to arrive. It was already a complete system, functioning according to the physical and chemical rules that govern water, heat, and matter. At night, standing on a cliff overlooking this ancient sea, you might hear only the steady sound of waves meeting rock. The darkness would stretch out over the water, broken only by the reflection of stars on the surface. With no ships, no lights, and no distant cities, the ocean would feel endless. A vast quiet presence connecting the far edges of the world. The tides, guided by the moon, would continue their slow rise and fall just as they do now. The moon itself was slightly closer to Earth during this era, which means tidal forces may have been stronger. This could have led to broader tidal ranges in some regions, exposing wide areas of the seafloor at low tide and flooding them again hours later. These cycles created dynamic environments along the coast where organisms had to adapt to changing conditions of water, air, and sunlight. Even simple life forms found ways to persist in these shifting zones, taking advantage of the nutrients and energy available during each phase of the tide. The deep ocean, far from these rhythmic changes, followed a steadier path. Here, temperature and light remained relatively constant, and life adapted to long-term stability rather than rapid variation. Chemical reactions in these depths proceeded slowly, influenced by the gradual mixing of water masses and the steady rain of particles from above. As Rodinia continued its long existence, the ocean remained both a boundary and a bridge. It separated the land from the rest of the planet's surface. Yet it also connected distant shores through currents and shared chemistry. A change in one region could over time influence conditions thousands of kilometers away. This interconnectedness is one of the ocean's most remarkable features. Even in a world with a single supercontinent, the sea acted as a unifying system carrying heat, matter, and life's building blocks around the globe. It was a quiet network, invisible from the surface, yet fundamental to the planet's balance. In the far future of Rodinia's timeline, the same forces that brought the continents together would begin to pull them apart. As cracks formed in the land, new ocean basins would open, allowing water to flood into fresh spaces. The single global sea would gradually become divided into separate bodies, setting the stage for the familiar arrangement of oceans we know today. But at this moment in our exploration, the ocean remains whole, wrapping the supercontinent in a continuous embrace. It is a world of slow motion and subtle change, of steady currents and layered sediments, of life that thrives quietly in water rather than striding across land. As you continue to listen, perhaps let your thoughts drift across that vast surface, following a current as it carries warm water away from the equator and sends cooler flows back in return. Imagine the long journey of a single grain of sand, eroded from a distant mountain, carried by a river into the sea, and finally settled on the ocean floor, where it will rest for millions of years before becoming part of the rock record. If you were to trace your path and land from Rodinia's wide, quiet shores and continue walking for days or even weeks, the land would gradually begin to change beneath your feet. The soft sediments of the coast would give way to firmer ground, to ancient layers of stone that told stories far older than any river or ocean. The horizon ahead would no longer feel entirely flat. Low rises would appear first, then distant ridges, and eventually the long-worn silhouettes of mountain ranges stretching across the unified world like slow, frozen waves of rock. These mountains were not born in moments of sudden violence. Their story unfolded in a way that is almost difficult to notice, even across many human lifetimes. The rise and fall of Rodinia's mountains followed a rhythm measured in millions of years, guided by the same deep forces that drew the continents together in the first place. To understand how these vast stone structures came to be, it helps to imagine the planet not as a solid shell, but as a layered system in constant, patient motion. Beneath the surface of the land lies the lithosphere, the rigid outer layer made up of Earth's crust and the uppermost part of the mantle. This layer is broken into massive plates that move slowly over the softer, warmer rock below. These plates drift at speeds no faster than the growth of a fingernail, yet over immense spans of time. That gentle motion becomes powerful enough to reshape the entire face of the planet. When two plates move toward one another, neither wants to give way easily. If both carry thick, buoyant continental crust, they collide and crumple. The rock at the edges has nowhere to go but up or down. Some of it is forced deep into the earth where heat and pressure change its structure. Some of it is pushed upward, folding and fracturing as it rises. This is how mountain belts begin. Not as sharp peaks, but as broad, uplifted regions that slowly grow taller as the pressure continues. Rodinia was formed by a series of these long collisions. Ancient continental fragments drifted together, closed the ocean basins that once separated them, and welded themselves into a single land mass. Along the seams where they met, enormous mountain systems took shape. These ranges likely stretched for thousands of kilom, forming chains of high ground that crossed the supercontinent's surface like the stitches in a vast geological quilt. At their youngest, these mountains may have rivaled or even surpassed the height of the Himalayas. Their slopes would have been steep, their peaks rugged, their valleys deep and narrow. Yet even at this early stage, the forces that would eventually wear them down were already at work. Wind swept across exposed ridges. Rain fell on bare rock, seeping into cracks and slowly breaking stone apart. Rivers gathered this loosened material and carried it away, grain by grain, toward lower ground and distant seas. This process of erosion is as much a part of mountain building as uplift itself. While tectonic forces push rock upward from below, weather and water pull it back down from above. The shape of any mountain range is a balance between these two opposing influences. One slow and relentless from the depths, the other equally persistent from the surface. In Rodinia's time, the absence of forests and complex plant life changed how erosion worked. Today, roots anchor soil, slow the flow of water, and stabilize slopes. Without that living net, rain could more easily wash loose material downhill. Rivers may have carried heavier sediment loads, and landscapes could shift more quickly in response to storms and seasonal changes. As sediment moved away from the mountains, it did not disappear. It settled in low-lying basins, river deltas, and shallow seas, forming thick layers of sand, silt, and mud. Over time, these layers were buried, compacted, and cemented into sedimentary rock. In this way, the worn-down remains of ancient peaks became the foundation of future landscapes, a quiet recycling of stone across geological time. The interior of Rodinia likely held vast plateaus and highlands formed from the roots of older mountain belts. These regions may have stood high above sea level for long periods, acting as sources of sediment and influencing climate patterns. High ground affects how air moves across the land, forcing winds to rise, cool, and drop their moisture on one side while leaving the other side drier. This creates rain shadows, regions where precipitation is limited because mountains block the passage of moist air. In Rodinia's interior, such effects could have led to broad arid zones far from the moderating influence of the surrounding ocean. These dry regions would have experienced wide temperature swings between day and night, and their landscapes would have been shaped primarily by wind and occasional intense rainfall rather than by steady streams. Along the edges of the supercontinent, mountain ranges played a different role. Here they often formed as the result of oceanic crust being forced beneath continental margins in a process known as subduction. As one plate slid beneath another, it melted and released fluids that rose into the overlying crust. This triggered volcanic activity, building chains of volcanoes that paralleled the coastline. These volcanic arcs added new material to the land, creating layers of lava and ash that eventually hardened into rock. Over time, these volcanic regions could merge with the continent itself, becoming part of the growing landmass. The combination of collision-driven mountains in the interior and volcano-driven mountains along the margins gave Rodinia a complex and varied topography. Deep within these mountain belts, rocks were transformed by heat and pressure into new forms. Limestone became marble. Sandstone became quartzite. Shells turned into slate and schist. These metamorphic rocks carried the imprint of the forces that shaped them. Their minerals aligned and recrystallized in response to stress. Today, geologists study these rocks to learn not just where mountains once stood, but how they formed and how intense the conditions were beneath the surface. The rise of mountains also influenced the chemistry of the planet. Exposed rock surfaces reacted with rainwater and air in a process known as chemical weathering. This process pulled carbon dioxide out of the atmosphere and locked it into minerals that were eventually carried to the ocean. Over long periods, this helped regulate Earth's climate, linking the growth of mountain ranges to shifts in global temperature. In times when tectonic activity was strong and mountains rose quickly, weathering rates increased. More carbon dioxide was removed from the air, which could lead to cooling. When uplift slowed and mountains were worn down, weathering decreased, allowing volcanic emissions to build carbon dioxide back up in the atmosphere and potentially warm the planet. In this way, the slow pulse of stone beneath Rodinia's surface was connected to the rise and fall of temperatures across the entire globe. If you were to stand on one of these ancient peaks and look out across the land, the view would be vast and open. The absence of tall vegetation would allow you to see far into the distance across plains, ridges, and valleys, shaped by long-forgotten rivers. The air would likely feel thinner at higher elevations, and the wind would move freely across exposed rock. Clouds might gather around the mountains, drawn upward by rising air currents. Rain would fall on the slopes, feeding streams that cut their way down toward the lands. In colder periods, snow and ice could cling to the highest elevations, adding another layer to the process of erosion as freezing and thawing broke rock apart. Over time, even the tallest peaks could be reduced to rolling hills. The sharp edges of young mountains softened. Valleys widened. What had once been dramatic landscapes became gentler, though no less vast. This cycle of growth and decay repeated again and again across Rodinia's long existence. Some mountain belts formed, rose, and were largely worn away before the supercontinent even began to break apart. Others persisted as highlands that influenced the paths of rivers and the distribution of sediment long after their tectonic origins had faded into the deep past. The deep roots of these ancient mountains remained hidden beneath the surface. Even as erosion lowered the visible landscape, the thickened crust below continued to float higher on the softer mantle, much like an iceberg floating in water. This process, known as isostasy, meant that as material was removed from the top, the crust could slowly rise to compensate, exposing deeper layers of rock. This is why some of the oldest rocks on Earth are found in regions that were once mountain cores. As the upper layers were stripped away, the deep metamorphosis roots were eventually revealed at the surface, offering a glimpse into conditions far below the ancient land. Rodinia's mountains also played a role in shaping the planet's waterways. Rivers tend to follow paths of least resistance, carving channels along fractures and low points in the rock. The arrangement of mountain belts guided the flow of water across the supercontinent, determining which regions drained toward which parts of the surrounding ocean. Some rivers may have crossed great distances, gathering water from broad catchment areas before finally reaching the sea. Others flowed into inland basins where water collected and evaporated, leaving behind salts and minerals. These basins could become sites of thick sediment accumulation, preserving records of climate and landscape change. From a distance, the surface of Rodinia might have looked like a mosaic of textures and tones. Darker bands of volcanic rock, lighter layers of sedimentary deposits, and the varied hues of metamorphic stone all contributed to a landscape that was visually rich even in the absence of green life. As time passed, the forces beneath the crust did not rest. Heat continued to build in certain regions, and the same slow motions that once brought continents together began to shift. Stresses accumulated within the supercontinent, especially along zones of weakness left behind by earlier collisions. Cracks formed, at first too small to notice, then gradually widening. In these rifts, the crust thinned and sank. Magma rose from below, filling the gaps and creating new rock. The land above responded by stretching and lowering, forming long val and shallow basins. These early signs of separation began to influence the mountain systems. Some ranges were split by rifts. Others were left stranded on the edges of newly forming margins. The once continuous belts of high ground became segmented, their histories diverging as the land around them began to move apart. Erosion continued its steady work, reshaping the changing landscape. Rivers adjusted their courses to new slopes and basins. Sediments filled the growing rift valleys. The cycle of uplift and wear took on new patterns as the supercontinent's unified structure began to loosen. It is worth pausing to consider how quiet all of this would have felt on the surface. There were no sudden collapses of entire ranges, no dramatic scenes of mountains tearing apart. The changes happened over spans of time so long that they would have been imperceptible to any single generation of living things, even if those things had been capable of noticing. Instead, the land shifted in a way that feels more like breathing than breaking. A slow expansion here, a gentle sinking there, a ridge growing a little higher over millions of years, a valley becoming a little deeper. To walk across Rodinia's mountains would have been to walk across time itself. Each layer of rock beneath your feet representing a chapter in a story far older than anything we usually imagine. The stone would carry the memory of ancient oceans, long-vanished collisions and deep transformations that took place far below the surface. Across the wide, stony surfaces of Rodinia's land and the quiet shallows of its surrounding seas. Life moved in ways that were almost impossible to notice unless you knew exactly where to look. There were no footprints in the dust, no calls echoing across valleys, no wings passing overhead. Instead, the living world existed mostly at a scale measured in micrometers rather than meters, in thin films and soft layers, in slow chemical exchanges rather than swift motion. This was a planet where simplicity ruled. Yet within that simplicity lay the beginnings of complexity that would one day reshape everything. The dominant inhabitants of this ancient world were microbes, tiny organisms that had already been shaping Earth's surface and atmosphere for billions of years by the time Rodinia came together. These were not a single kind of life, but a vast collection of different forms, each adapted to particular conditions. Some thrived in sunlight, using its energy to split water molecules and release oxygen. Others lived in darkness, drawing energy from chemical reactions involving sulfur, iron, or methane. Together, they formed the foundation of nearly every ecosystem on the planet. In shallow coastal waters where sunlight could still reach the seafloor, microbial communities often gathered into dense layered structures known as mats. These mats were not random assemblies. They were carefully organized systems with different types of microbes occupying different layers, depending on their needs and tolerances. At the very top, closest to the light, lived photosynthetic organisms, often cyanobacteria, which captured sunlight and produced oxygen. Beneath them, in slightly darker and lower oxygen zones, lived microbes that used different chemical pathways to survive. Deeper still were organisms adapted to conditions, that would have been toxic to most life today. Over time, these mats trapped tiny particles of sediment carried by water and wind. As the microbes grew and divided, they bound these particles together, creating thin, stable layers. Slowly, these layers built up into structures that could rise above the surrounding seafloor, forming rounded or column-like shapes known as stromatolites. These formations are among the oldest visible signs of life on Earth. And during Rodinia's time, they were likely widespread along coastlines and in shallow seas. If you were to kneel beside one of these ancient mats, you might see a surface that looked smooth and dark, perhaps slightly textured, almost like damp leather stretched across the ground. It would not move in any obvious way, but beneath that surface, millions of tiny lives were constantly at work, exchanging chemicals, dividing, and responding to changes in light and water. The presence of these mats had a direct effect on the planet's chemistry. By producing oxygen, photosynthetic microbes contributed to the gradual increase of this gas in the atmosphere and the ocean. This was not a fast process. For a long time, oxygen reacted with minerals in the rocks and dissolved substances in the water, becoming locked away rather than accumulating in the air. Only after these sinks were gradually filled did oxygen begin to build up more noticeably. This slow rise in oxygen levels changed the conditions under which life could survive. Some microbes were harmed by oxygen, as it disrupted their internal chemistry. Others learned to use it, finding that oxygen-based metabolism allowed them to extract more energy from their environment. This shift set the stage for the evolution of more complex forms of life, though that transition was still far in the future during most of Rodinia's existence. Not all life was confined to the ocean. On land, especially in damp areas near rivers, lakes, or coastal margins, microbial communities found ways to persist. Thin films of life could grow on rock surfaces, in small pools of water, or in moist soil. These early land-based ecosystems were fragile, easily disturbed by changes in weather or the movement of sediment, but they represented an important step in life's gradual expansion beyond the sea. These terrestrial microbes played a role in breaking down rock through a process known as biological weathering, by releasing organic acids and other compounds. They helped dissolve minerals, making nutrients available both to themselves and to the surrounding environment. Over long periods, this contributed to the formation of soil-like materials. Though true soils, as we know them today, rich in organic matter and structured by plant roots, would not appear until much later. The oceans themselves were not uniform environments. Conditions varied with depth, distance from shore, and local chemistry. In sunlit surface waters, photosynthetic life could forming the base of simple food webs. In deeper or more stagnant waters where oxygen was scarce, different communities dominated, relying on chemical energy rather than light. In some regions, particularly near hydrothermal vents on the seafloor, life was supported by the constant flow of warm, mineral-rich fluids from beneath the crust. These environments offered a steady supply of chemicals like hydrogen sulfide and iron, which certain microbes could use as energy sources. Even in complete darkness, these organisms formed the foundation of localized ecosystems, demonstrating that sunlight was not the only path to survival. The presence of such varied environments encouraged experimentation in life's forms and functions. Different microbes developed different strategies for movement, attachment, and interaction with their surroundings. Some formed long chains or filaments. Others produced protective coatings or shells made of minerals. These adaptations allowed them to colonize new niches and withstand changing conditions. Among this world of microscopic life, hints of something more complex were beginning to appear. Fossil evidence from the late Proterozoic suggests that simple multicellular organisms may have existed during or shortly after Rodinia's time. These were not animals in the modern sense, but soft-bodied forms that grew as sheets, tubes, or small organized clusters of cells. Such organisms likely lived in shallow marine environments where conditions were relatively stable and nutrients were available. Their bodies did not have hard parts, which means they were not easily preserved in the fossil record. As a result, much of what scientists know about them comes from rare impressions left in fine sediments, where their shapes were briefly captured before being buried and transformed into rock. The emergence of multicellularity represented a significant shift. A single-celled organism lives and acts as one unit. A multicellular organism, by contrast, consists of many cells working together, often specializing in different tasks. This requires new ways of coordinating growth, communication, and response to the environment. During Rodinia's era, these early multicellular forms were likely simple, but they carried the seeds of future complexity. They experimented with size, shape, and structure, exploring what was possible within the constraints of their world. Some may have been little more than flat mats of cells, while others formed small, three-dimensional bodies anchored to the seafloor. The presence of oxygen in the environment was an important factor in this transition. Oxygen allows for more efficient energy production within cells, which can support larger and more complex bodies. As oxygen levels slowly increased, it may have opened the door for these early multicellular organisms to survive and diversify. Interactions between microbes and these emerging forms of life were likely subtle but significant. Microbial mats could provide both food and a stable surface for large organisms to attach to. In turn, the movement or growth of multicellular forms could disturb the mats, creating new patterns of nutrient flow and chemical exchange. Predation in the modern sense was probably minimal or absent. Most organisms either absorbed nutrients directly from their surroundings or fed on simple organic matter. The complex food webs that characterize later eras, with animals hunting and consuming one another, had not yet developed. This made the pace of ecological change slow and steady rather than dynamic and competitive. The lack of large, mobile life also meant that the physical structure of environments remained relatively undisturbed. Sediments could settle in calm layers. Microbial mats could grow undisturbed for long periods. The seafloor and shallow waters were shaped primarily by physical forces like waves, currents, and gravity, rather than by the activities of burrowing or grazing animals. This stillness is reflected in the rock record. Sedimentary layers from this time often show fine, undisturbed laminations, indicating that the sediments were not mixed or churned by living creatures. In later periods, when animals began to burrow and move through the seafloor, these neat layers became disrupted, creating a more chaotic pattern. Life during seafloor age was also closely tied to the chemistry of the water and air. Small changes in oxygen levels, nutrient availability, or temperature could shift. Which organisms thrived and which struggled. Because ecosystems were relatively simple, they could respond quickly to environmental changes. But they were also vulnerable to extremes. During colder periods, when ice spread across large areas of the ocean, sunlight reaching the water below was reduced. This would have limited photosynthesis, potentially lowering oxygen production and altering the balance of life in affected regions. In warmer times, increased weathering on land could deliver more nutrients to the sea, stimulating microbial growth in coastal waters. These cycles created a dynamic, though subtle interplay between the planet's physical state and its living systems. The land, the ocean, the atmosphere, and life itself were all part of a connected network, each influencing the others over long spans of time. On land, the presence of microbial communities may have influenced how landscapes evolved. By stabilizing sediments and contributing to chemical weathering, they helped shape the surface in ways that purely physical processes might not have achieved alone. Over millions of years, this biological influence became part of the planet's geological story. The simplicity of this world can be misleading. While individual organisms were small and often simple in structure, the systems they formed were complex in behavior. Chemical cycles linked distant environments. Biological activity influenced atmospheric composition. Geological processes created new habitats and removed old ones. All of this unfolded without any central control, guided only by the laws of physics and chemistry and the capacity of life to adapt. It is also worth considering how limited the sensory world of these organisms would have been. Without eyes, ears, or nervous systems, most microbes experienced their surroundings through chemical gradients and physical contact. Light was detected not as an image, but as an energy source. Movement was guided by changes in temperature, nutrient concentration, or chemical signals. For the earliest multicellular organisms, sensation may have been only slightly more complex. They might have been able to respond to touch or changes in light and water flow, but they did not perceive the world in anything like the way animals do today. Their existence was closer to being than to experiencing, focused on growth, maintenance, and reproduction rather than on exploration or interaction. Despite this, their presence marked an important shift. A body made of many cells can create internal environments, control the flow of substances within itself, and develop structures that allow it to interact with the outside world in new ways. These capabilities would over time lead to the emergence of tissues, organs, and eventually nervous systems. The path from microbial mats to complex animals was not a straight line. It involved many experiments, many dead ends, and long periods of relative stability. Rodinia's time sits in the middle of this journey, a phase where the groundwork was being laid, even if the final outcome was still far beyond the horizon. Standing at the edge of a shallow sea during this era, you might see the water's surface ripple gently in the wind. Beneath it, just visible through the clear shallows, would be dark patches of microbial mats clinging to the seafloor. Tiny bubbles of gas might rise occasionally, a sign of chemical reactions taking place below. There would be no obvious movement, no flashes of color or darting shapes. Yet in that quiet scene, the processes that would eventually lead to forests, reefs, and animals were already in motion. Cells were dividing. Genes were mutating. New forms were being tested in the slow laboratory of time. As Rodinia continued its long existence, the environments that supported this simple life were gradually changing. The atmosphere was slowly gaining oxygen. The climate shifted between warmer and colder states. The land itself was beginning to feel the first signs of stress that would one day pull it apart. All of these changes created new challenges and new opportunities for living things. Some forms would fade away. Others would adapt and persist. A few would give rise to lineages that would carry life into a very different future. Long stretches of Rodinia's surface lay beneath a sun that looked familiar, yet behaved in ways that shaped a very different world. The light that reached the ground followed the same daily arc from horizon to horizon. But the planet receiving it was arranged in a way that changed how warmth, wind, and water moved across its face. Climate during this time was not just a matter of how strong the sun shone. It was the result of a careful balance between the position of a single vast land mass, the chemistry of the atmosphere, the circulation of a global ocean, and the slow, steady turning of the Earth itself. The sun in the deep Proterozoic was slightly dimmer than it is today. Its energy output was lower by a noticeable margin, which on its own might suggest a colder planet. Yet Rodinia was not locked in permanent ice. Liquid water flowed across the land, and oceans remained open over much of the globe for long periods. This apparent contradiction is explained by the composition of the atmosphere, which acted as a blanket trapping heat and reducing the amount of energy that escaped back into space. Carbon dioxide and methane played a central role in this process. Both gases are effective at absorbing infrared radiation, the type of energy the Earth releases after being warmed by sunlight. When these gases were present in higher concentrations, they helped retain heat near the surface, countering the sun's lower output. Over millions of years, the balance between volcanic emissions, which added these gases to the air, and weathering processes which removed them shaped the planet's long-term temperature trends. The presence of a single supercontinent added another layer of complexity. Land and water respond differently to sunlight. Land heats up quickly and cools down just as fast, while water warms and cools more slowly. With so much land concentrated into one continuous mass, Rodinia created strong contrasts between its interior and its surrounding ocean. During the day, sunlight warmed the surface of the supercontinent, causing air near the ground to rise. This rising air created areas of low pressure that drew in cooler, moisture-laden air from the ocean. At night, the land cooled rapidly, and the pattern reversed, sending air back toward the sea. This daily cycle of heating and cooling generated persistent wind systems along the continent's margins. These winds carried moisture inland, but their influence weakened with distance from the coast. As air traveled farther across the supercontinent, it lost much of its water through rainfall. This meant that central regions of Rodinia were likely drier than areas closer to the ocean, creating broad zones of aridity far from any moderating influence. Seasonal changes added still more variation depending on the supercontinent's orientation and position on the globe. Different parts of Rodinia experienced shifts in sunlight over the course of the year. Regions closer to the equator received relatively consistent solar energy, while those at higher latitudes saw stronger contrast between bright, warmer seasons and darker, cooler ones. These changes influenced where clouds formed and where rain fell. In warmer periods, increased evaporation from the surrounding ocean added more moisture to the atmosphere. Winds carried this moisture onto the land where it condensed into clouds and fell as rain, especially along windward coasts and mountain slopes. In cooler periods, evaporation slowed and the air held less water, reducing precipitation across much of the supercontinent. The shape of Rodinia's terrain further guided these patterns. Mountain ranges forced air upward as winds crossed them. As rising air cooled, it released moisture, creating wetter conditions on the windward side and drier conditions on the leeward side. This process, known as the rain-shadow effect, likely produced long, dry regions in the interiors of the supercontinent, where rivers were fewer and landscapes were shaped more by wind than by flowing water. Rivers that did exist often followed long, winding paths, collecting water from wide catchment areas before finally reaching the sea. Their flow varied with the seasons, swelling during wetter periods and shrinking during dry spells. These cycles influenced how sediment was moved across the land and deposited along coastlines and in shallow seas. The global ocean surrounding Rodinia played a steadying role in the climate system. Water's ability to store heat helped moderate temperature extremes, especially in coastal regions. Ocean currents carried warm water away from equatorial zones and brought cooler water back in return, redistributing energy around the planet. However, the presence of a single massive land barrier altered the usual pathways of these currents. Instead of weaving through gaps between continents, water flowed in broad loops around the supercontinent's edges. This circulation pattern affected where heat was released into the atmosphere and where cooler conditions prevailed. In some periods, this system may have contributed to dramatic shifts in climate. Geological evidence suggests that Earth experienced several global or near-global glaciations during the time Rodinia existed. These events, often referred to as snowball Earth episodes, were times when ice sheets may have covered large portions of the planet's surface, possibly extending close to the equator. The onset of such cold periods likely involved a combination of factors. When large areas of land were exposed to weathering, Especially in warm, wet conditions, carbon dioxide was removed from the atmosphere more quickly. This reduced the greenhouse effect, allowing more heat to escape into space. As the planet cooled, ice began to spread. Ice reflects a large portion of incoming sunlight back into space, a property known as albedo. As more ice formed, less solar energy was absorbed by the surface, leading to further cooling and more ice growth. This feedback loop could drive the planet into a deeply frozen state. During these times, much of the ocean's surface may have been covered by ice. Beneath that frozen layer, however, liquid water continued to exist. Heat from the Earth's interior and from the slow movement of ocean currents prevented the sea from freezing solid. Life persisted in these sheltered waters, even as conditions on the surface became harsh. Volcanic activity played a role in ending these cold episodes. Even as ice spread, volcanoes continued to release carbon dioxide into the atmosphere. With weathering slowed by the cold and ice-covered land, less of this gas was removed. Over millions of years, carbon dioxide accumulated, strengthening the greenhouse effect until the planet warmed enough for the ice to begin melting. As ice retreated, darker surfaces of land and water absorbed more sunlight, accelerating the warming. This rapid shift from cold to warm conditions would have dramatically altered the environment, reshaping landscapes and affecting the distribution of life across the planet. Between these extremes of deep cold and relative warmth, Rodinia's climate likely experienced long periods of stability. During these times, patterns of wind, rainfall, and temperature settled into rhythms that persisted for millions of years. Microbial communities and early multicellular life adapted to these conditions, finding niches in shallow seas, damp coastal zones, and sheltered inland waters. The length of a day also influenced climate patterns. During the Proterozoic, Earth rotated slightly faster than it does now, making days shorter. This faster rotation affected the behavior of the atmosphere, strengthening certain wind systems, and shaping the way air moved between equator and poles. These wind patterns influenced the formation of large-scale circulation cells, similar in concept to the Hadley cells that operate on the modern Earth. Warm air rose near the equator, moved toward higher latitudes, cooled and sank, creating belts of prevailing winds. The exact positions and strengths of these systems depended on Rodinia's location and the distribution of land and sea. The supercontinent's vast interior may have experienced more extreme seasonal temperature changes than coastal areas. Without nearby ocean water to buffer heat and cold, temperatures could swing widely between warmer and cooler periods. These variations influenced how rocks weathered, how rivers flowed, and where life could find stable conditions. Dust played a subtle but important role in this climate system. Winds sweeping across dry, open landscapes lifted fine particles into the air. These particles could travel long distances before settling, influencing cloud formation and the way sunlight was scattered. In some cases, dust falling into the ocean may have delivered nutrients that supported microbial growth in surface waters. The relationship between climate and life was closely intertwined. Warmer, wetter periods supported more extensive microbial mats in shallow seas and along coastlines. Cooler, drier times limited the availability of liquid water and sunlight, reducing the productivity of these ecosystems. Over long time scales, these shifts created patterns of expansion and contraction in living communities. Some regions became centers of biological activity, while others fell into relative quiet. The distribution of life across Rodinia was not fixed, but followed the slow pulse of climate change. It is also likely that climate influenced the chemistry of the oceans and atmosphere in ways that fed back into the system. Changes in temperature affected how gases dissolved in water. Variations in rainfall altered the delivery of minerals and nutrients from land to sea. These factors in turn influenced biological activity, which could change the composition of the atmosphere. From a surface perspective, the experience of weather on Rodinia would have felt both familiar and unfamiliar. Winds would still blow, clouds would still gather, and rain would still fall. Yet the patterns behind these events were shaped by a world with no forests, no grasslands, and no animals to alter the flow of air and water. Storms may have swept across coastal regions, driven by the contrast between warm ocean air and cooler land surfaces. Lightning would have flashed across the sky, and thunder would have rolled across open plains and bare hills. In inland areas, long periods of calm might have been punctuated by sudden intense rainfall, carving channels into dry ground and filling temporary lakes and basins. At higher latitudes or elevations, snow and ice would have appeared during cooler periods, shaping the land through freezing and thawing. Glaciers, where they formed, moved slowly across the surface, grinding rock beneath them and leaving behind distinctive patterns of erosion and sediment. The overall effect of these processes was a planet in constant, though measured, motion. Climate did not remain fixed. It shifted in response to changes in atmospheric composition, tectonic activity, and the position of the supercontinent on the globe. Each shift left its mark on the land, the ocean, and the living systems that depended on them. To imagine standing on Rodinia during one of its warmer phases is to picture a wide, open landscape under a sky filled with slow-moving clouds. The air carries warmth from the sun, and a steady breeze moves in from the distant sea. Rivers flow across broad plains, and shallow coastal waters host dark patches of microbial life. To imagine the same place during a colder phase is to see a very different scene. Ice may cover nearby ground. The air feels sharper and drier. The sun's light reflects off pale surfaces, and the world takes on a quieter, more subdued tone. Both scenes are part of the same long story. Chapters written not in years or centuries, but in spans of time that stretch beyond easy comprehension. The climate of Rodinia was not a single state, but a sequence of conditions shaped by slow, interconnected processes. Think about how the warmth you feel from the sun today connects to that ancient light. The same star following the same path across the sky has warmed a planet that has changed its shape, its air, and its life many times over. There are moments in Earth's long past when the planet seems to pause, not in motion, but in mood, settling into a state so different from what we know that it feels almost like another world entirely. During Rodinia's time, one of those moments arrived in the form of deep, widespread cold. An era when ice extended across landscapes and seas, and the supercontinent found itself wrapped in a quiet, reflective shell. This period, often called Snowball Earth, was not a single event, but a series of long, drawn-out episodes when the balance between warmth and cold tipped heavily toward the latter. To imagine this world, it helps to begin with the familiar. Think of the coldest winter morning you can remember. The air feels sharper, sounds carry differently, and the ground seems to hold its breath beneath a pale layer of frost or snow. Now take that sensation and stretch it across not just a season, but thousands, perhaps millions of years, and across not just a region, but much of the planet itself. The cooling of Earth during Rodinia's age did not happen overnight. It followed the same slow, interconnected processes that shaped the climate in warmer times. Volcanic activity, weathering of rock, ocean circulation, and the chemistry of the atmosphere all played their parts in a long and complex sequence. One of the key drivers behind these cold episodes was the gradual removal of carbon dioxide from the air. As Rodinia's mountains rose and were exposed to wind and rain, chemical reactions between water and rock became more active. Rainwater, slightly acidic because it absorbed carbon dioxide from the atmosphere, reacted with minerals in the stone, breaking them down and forming new compounds. The products of these reactions were carried by rivers into the ocean, where they eventually became part of sediments on the seafloor. This process locked carbon away in solid form, reducing the amount of this greenhouse gas in the atmosphere. With less carbon dioxide to trap heat, more of the sun's energy escaped back into space, and the planet began to cool. As temperatures fell, ice started to form in regions that were already prone to cold, such as high latitudes and elevated areas. Glaciers crept down mountain sides and spread across plains. Sea ice began to form at the edges of the global ocean. At first, these changes were local, but they set in motion a powerful feedback loop. Ice and snow reflect sunlight very effectively. When the surface of the planet becomes lighter, more of the incoming solar energy is bounced back into space, rather than absorbed and converted into heat. This reflection, known as the albedo effect, leads to further cooling, which allows more ice to form, which in turn reflects even more sunlight. Over time, this cycle can accelerate, pushing the planet toward a state where ice covers not just the poles, but much of the surface, possibly extending all the way to equatorial regions. In such a scenario, Rodinia's wide plains, mountain slopes, and coastal zones would have been blanketed in white, and the ocean surface would have been sealed beneath thick layers of ice. From above, Earth during one of these deep, cold periods might have looked like a pale, shining sphere. Its darker features muted beneath a continuous layer of frost and ice. The contrast between land and sea would have been harder to see, as both took on similar tones under the frozen cover. On the ground, the experience would have been one of stillness. Wind would still move across the ice, carrying fine, dry snow in long, low drifts. The sun lower in the sky during colder seasons or at higher latitudes would cast a cold, bright light across the landscape, creating sharp reflections and long shadows. Rivers which in warmer times carried water and sediment across the land would have slowed or frozen entirely. Some may have continued to flow beneath ice, carving channels in the rock below, but their influence on the surface would have been limited. Lakes and shallow seas would have been sealed over, turning into flat, reflective expanses of frozen water. Despite this apparent stillness, the planet beneath the ice did not stop. Heat from Earth's interior continued to rise through the crust. In some places, this heat may have melted ice from below, creating pockets of liquid water beneath the frozen surface. These hidden environments offered refuge for life, allowing it to persist even when conditions above were harsh. The ocean, too, remained active beneath its icy lid. While the surface froze, deeper waters retained their warmth and continued to circulate, driven by differences in temperature and salinity. This slow movement carried nutrients and dissolved gases through the global sea, maintaining chemical connections between distant regions. Life during Snowball Earth did not vanish. Microbes, especially those adapted to cold or low-light conditions, found ways to survive in sheltered environments. Some lived in cracks within the ice where sunlight could penetrate and melt small pockets of water. Others thrived near hydrothermal vents on the seafloor, drawing energy from chemical reactions rather than from the sun. In shallow coastal regions where ice might have been thinner or periodically broken by currents and tides, photosynthetic organisms could still find enough light to carry out their processes. These small patches of productivity may have been crucial in maintaining oxygen production and supporting other forms of life. The land itself, beneath its icy cover, continued to change. Glaciers, heavy and slow-moving, ground against the rock below, scraping away layers of stone and carrying debris with them. As they advanced and retreated, they reshaped the landscape, carving valleys, smoothing ridges, and leaving behind deposits of sediment in their wake. When ice sheets reached the ocean, they could break apart, sending large pieces of ice drifting into the water. As these icebergs melted, they dropped the rocks and sediment they carried, creating distinctive patterns on the seafloor that scientists still find in ancient deposits. These glacial features serve as some of the strongest evidence for Snowball Earth conditions. Today, geologists discover rock formations in regions that are now warm and temperate, yet show clear signs of having been shaped by ice. This suggests that cold conditions once extended far beyond the polar zones, supporting the idea of a planet-wide or near-planet-wide freeze. The atmosphere above this frozen world also reflected the changes below. With much of the land and ocean covered in ice, the exchange of gases between the surface and the air was reduced. Photosynthetic activity in open water and on land decreased, slowing the production of oxygen. At the same time, volcanic activity continued to release carbon dioxide into the atmosphere. Even in a frozen world, volcanoes did not stop erupting. Gases rose from Earth's interior and entered the air, gradually building up because the usual processes that removed carbon dioxide, such as chemical weathering of exposed rock, were slowed or halted by the cold and the ice cover. Over millions of years, this accumulation of greenhouse gases began to change the balance again. As carbon dioxide levels increased, the atmosphere became more effective at trapping heat. The planet slowly warmed, even though much of its surface remained frozen. Eventually, a tipping point was reached. The warming became strong enough to begin melting ice near the equator, or in regions where the ice was thinnest. As dark surfaces of water or land were exposed, they absorbed more sunlight than the surrounding ice, leading to further warming and more melting. This created a powerful reversal of the earlier feedback loop. Instead of ice reflecting sunlight and promoting cooling, open water and bare ground absorbed heat and promoted warming. The process accelerated, and the planet began to emerge from its frozen state. The transition from snowball Earth conditions to a warmer world may have been relatively rapid in geological terms. What took millions of years to develop could have been undone in a much shorter span, perhaps thousands of years or less. Ice sheets retreated. Rivers resumed their flow. The ocean surface opened up, allowing the exchange of gases and heat with the atmosphere to increase dramatically. This sudden influx of melt water and the renewed weathering of exposed rock delivered large amounts of minerals and nutrients to the ocean. These inputs may have fueled bursts of biological activity, allowing microbial communities to expand and diversify in the newly favorable conditions. The end of a snowball Earth episode would have transformed the landscape. Glacial valleys filled with water becoming lakes or seas. Thick layers of sediment left behind by retreating ice created new plains and lowlands. Coastlines shifted as sea levels changed, flooding some areas and exposing others. For life, these changes represented both challenges and opportunities. Environments that had been stable for long periods were suddenly altered. Some organisms may have struggled to adapt, while others took advantage of the new conditions to spread into freshly available habitats. The repeated cycle of deep cold and subsequent warming likely played a role in driving evolutionary change. Stressful conditions can act as filters, favoring organisms that can survive extremes. When conditions improve, these survivors can expand and diversify, potentially leading to new forms of life. In the context of Rodinia's long existence, snowball Earth episodes were dramatic interludes, moments when the planet's usual rhythms were pushed to their limits. They did not last forever, but their effects rippled forward through time, influencing the chemistry of the ocean and atmosphere, the shape of the land, and the trajectory of life itself. From a modern perspective, it is striking to think of a world where ice might have reached tropical latitudes, where the line between land and sea was hidden beneath a continuous frozen surface. Such a planet challenges our sense of what is normal or possible, reminding us that Earth's history includes states far outside our everyday experience. The quiet of this frozen world would have been profound. With much of the surface sealed beneath ice, the usual sounds of wind through water or waves against rock would have been muffled. The landscape would have been dominated by the subtle noises of shifting ice. The occasional crack or groan as glaciers moved and adjusted to the ground below. At night, the sky above this pale surface would have been clear and sharp, especially in regions where cold, dry air-limited cloud formation. Stars would have reflected off the ice, creating a sense of light even in darkness. The moon, slightly closer to Earth than it is now, would have cast bright, cold shadows across the frozen plains. Beneath all of this, deep in the ocean and within the crust, the planet's internal heat continued its slow, steady work. The mantle flowed. Plates shifted. New rock formed at hidden ridges. Even in a time of surface stillness, the deep engine of the Earth remained active, preparing for the next phase of change. As Rodinia moved through these cycles of freezing and thawing, its structure was also being influenced by tectonic forces. The same stresses that would eventually pull the supercontinent apart were building. Even as ice covered much of its surface, cracks formed in the crust, magma rose in some regions, and the foundations of future oceans began to take shape. This overlap of deep cold and deep motion adds another layer to the story. The surface of the planet might have seemed locked in ice, but beneath that shell, the processes that would reshape the world were already in motion. The memory of Snowball Earth is preserved in rocks scattered across today's continents. Layers of glacial deposits, unusual chemical signatures, and distinctive sediment patterns all serve as reminders of these ancient cold periods. By studying these clues, scientists piece together a picture of a planet that once tested the limits of its own stability. It is a story of balance and imbalance, of feedback loops that can push the system toward extremes, and of slow, persistent forces that eventually guide it back again. In this way, the long quiet of ice becomes part of a larger narrative about how Earth regulates itself over immense spans of time. From the high ground where ancient ridges met the wide sky, thin threads of water began their long, patient journeys across the surface of Rodinia. These were not the familiar rivers we picture today, lined with trees or crossed by bridges, but broad shifting pathways shaped entirely by stone, gravity, and the quiet pull of the distant sea. On a world where nearly all land was joined into a single immense mass, water did not recognize borders or boundaries. It followed the contours of the planet itself, carving routes that could stretch across thousands of km before finally meeting the global ocean. Rainfall, when it came, was the starting point for these vast systems. Moist air carried in from the surrounding sea rose over mountains and highlands, cooled, and released its water back onto the land. Some of that water soaked into the ground, filling cracks and pores in the rock. The rest gathered on the surface, forming small streams that merged into larger channels. Over time, these channels became the arteries of Rodinia's landscape, carrying not only water, but the very substance of the land itself. Because the supercontinent was so large, many rivers traveled through a wide range of environments. A single river might begin in a cool, elevated region, where snow and seasonal rain fed its headwaters. From there, it could descend through rocky valleys, spread across open plains, and eventually wind through low-lying basins before reaching the distant coast. Each stage of that journey shaped the river's character and the land around it. In the uplands, water moved quickly. Steep slopes gave streams the energy to cut into rock, forming narrow valleys and deep channels. Loose fragments of stone were carried along, bouncing and grinding against the riverbed. This constant abrasion slowly wore down the landscape, reducing mountains and hills into sediments that would be transported far from their source. As rivers reached flatter terrain, their pace slowed. Channels widened and deepened, and water began to meander across the land. Instead of cutting straight down, the river shifted from side to side, eroding one bank while depositing sediment on the other. Over long periods, this movement created broad floodplains, areas of relatively flat land shaped by repeated cycles of flooding and retreat. These floodplains were dynamic places. During wetter periods, rivers could overflow their banks, spreading water and fine sediment across the surrounding land. When the water receded, it left behind a thin layer of minerals and particles that gradually built up the ground. This process created fertile environments for microbial life, especially in shallow pools and damp soils where thin films of water lingered. Because there were no deep-rooted plants to stabilize the soil, Rodinia's rivers likely carried heavy sediment loads. Rainfall could wash loose material directly into channels, and wind sweeping across dry regions could deliver fine dust that eventually settled into the water. This made many rivers cloudy and rich in suspended particles, giving them a different appearance and texture than many modern streams. The movement of sediment was not just a surface phenomenon. It was part of a larger cycle that linked mountains, plains, and oceans into a single system. Material eroded from high ground was carried downstream, deposited in lowlands, and eventually transported to the sea. There, it settled onto the seafloor, becoming part of the sedimentary layers that recorded the planet's history. Some rivers did not reach the ocean at all. In the vast interior of the supercontinent, water could flow into low-lying basins where it collected and evaporated. These inland seas or large lakes left behind salts and minerals as the water disappeared, creating distinctive chemical deposits. Over time, these areas could become flat, dry expanses marked by layers of evaporate minerals. The existence of such closed basins added variety to Rodinia's hydrological system. They created regions where water chemistry differed from that of the global ocean, influencing the types of microbial life that could survive there. Some organisms adapted to high salinity or unusual chemical conditions, forming specialized communities in these isolated environments. Seasonal changes shaped the behavior of rivers as well. In regions where rainfall varied over the year, channels could swell during wet periods and shrink during dry ones. During floods, rivers gained the power to reshape their surroundings dramatically, carving new paths, filling old channels, and redistributing large amounts of sediment in a relatively short time. In drier seasons, water levels dropped, exposing wide stretches of riverbed. Pools of standing water could remain in low spots, providing refuges for microbial life and simple multicellular organisms. These shifting conditions created a mosaic of habitats that changed over time, offering both stability and challenge for the living systems that depended on them. The direction and pattern of river networks were guided by the shape of the land. Mountain ranges acted as divides, determining which way water would flow. A ridge could separate two drainage systems, sending rainfall on one side toward one part of the ocean and on the other side toward a completely different region. Because Rodinia was so large, some of these drainage systems were immense. A single wedge could cover an area comparable to entire modern continents. This meant that changes in one part of the system, such as increased erosion from a mountain range or shifts in rainfall patterns, could influence conditions far downstream. Rivers also played a crucial role in shaping the chemistry of the ocean. As water flowed across the land, it picked up dissolved minerals from the rocks it passed over. These included elements like calcium, magnesium, and silica, as well as nutrients such as phosphorus and nitrogen compounds. When this mineral-rich water reached the sea, it altered the composition of coastal waters. These inputs supported the growth of microbial communities, particularly in shallow regions where sunlight was available. In this way, rivers acted as connectors between the solid land and the living ocean, delivering the raw materials that life used to build its structures and carry out its processes. The paths of rivers were not fixed forever. Tectonic activity slowly changed the shape of the land, lifting some regions and lowering others. A gentle uplift in one area could divert a river's course, sending it along a new path. Over millions of years, entire drainage systems could be reorganized as the supercontinent's surface evolved. Glacial periods added another layer of influence. When ice spread across parts of the land, rivers were blocked or redirected. Meltwater from glaciers created powerful flows that carved new channels and deposited large amounts of sediment in a relatively short time. As the ice retreated, these meltwater rivers often left behind wide valleys and thick layers of gravel and sand. In colder regions, water flowing beneath ice sheets could carve tunnels and channels in the rock, shaping the land in ways that were only revealed long after the ice disappeared. These hidden processes left subtle marks that scientists still study to understand the behavior of ancient glaciers and the rivers they fed. Along the coast, where rivers met the global ocean, the interaction between fresh and salt water created complex environments. Sediment carried by rivers spread out into the sea, forming deltas and shallow shelves. These areas were shaped by the balance between the river's flow and the action of waves and tides. In times of high river discharge, deltas could grow outward, extending the land into the sea. During periods of lower flow or stronger wave action, these deposits could be reworked and redistributed along the coast. Over long periods, this constant adjustment created layered sequences of sediment that recorded changes in climate, sea level, and river behavior. The tidal influence on rivers may have been particularly noticeable during Rodinia's time. The moon, slightly closer to Earth, exerted stronger gravitational forces, which could have led to broader tidal ranges in coastal areas. This meant that the boundary between river and ocean shifted back and forth over wide zones, creating environments that were alternately flooded and exposed. These tidal zones were dynamic places where fresh and salt water mixed, and where sediments were constantly moved and reshaped. Microbial mats could grow on exposed surfaces during low tide and be submerged again as the water returned. This cycle created layered structures in the sediment, preserving records of repeated environmental changes. The soundscape of Rodinia's rivers would have been simple and steady. Water flowing over stone, wind moving across open channels, and the occasional rumble of shifting sediment during floods would have been the dominant notes. Without animals or plants to add their own voices, the rhythm of moving water would have stood out against the broader quiet of the landscape. At night, rivers might have reflected starlight in long, narrow bands, their surfaces dark and smooth in calmer stretches, broken into shimmering patterns where water flowed more quickly. The absence of artificial light and dense vegetation would have made these reflections more visible, connecting the surface of the land to the sky above. In subtle ways, the presence of rivers also influenced the distribution of life across Rodinia. Even in a world dominated by microbes, water provided stability and opportunity. Shallow, slow-moving sections of rivers could host microbial communities that differed from those in the ocean or in standing inland waters. Nutrients delivered by upstream erosion created conditions that supported higher levels of biological activity in certain regions. These areas could become centers of growth where microbial mats spread across the riverbed and along the banks, creating patches of life in an otherwise rocky landscape. Early multicellular organisms, where they existed, may have found these environments particularly favorable. The combination of flowing water, nutrient availability, and moderate conditions offered a balance between stability and change, allowing simple soft-bodied forms to attach, grow, and reproduce. The long paths of rivers also served as corridors for chemical exchange. Substances dissolved in water were carried from one region of the supercontinent to another, linking distant environments into a shared system. A change in rock chemistry in one area could over time influence the composition of water and sediments far downstream. In this way, rivers acted as the veins of Rodinia, circulating materials across its surface and tying together mountains, plains, basins, and seas into a single interconnected network. They were not just features of the landscape, but active participants in the planet's ongoing transformation. As tectonic forces slowly built tension within the supercontinent, subtle changes began to appear in the drainage patterns. New low points formed where the crust stretched and thinned. Existing rivers were drawn toward these areas, adjusting their courses to follow the changing slopes. These early rift zones collected water and sediment, becoming long, shallow basins that hinted at future oceans. Rivers that once flowed toward the outer margins of Rodinia began to feed these internal depressions instead, marking the first stages of the supercontinent's eventual separation. Erosion continued its quiet work, lowering high ground and filling low areas. The contrast between source and sink, between mountain and sea, gradually softened. Yet the overall structure of the land remained, shaped by the deep forces beneath the crust. To picture Rodinia's rivers is to picture movement without hurry. Water followed gravity. Gravity followed the shape of the land, and the land followed the slow shifting of tectonic plates. Each step in this chain operated on its own time scale, from the quick rush of a flood to the million-year rise of a mountain range. Imagine standing beside one of these ancient rivers. The channel stretches away into the distance, its surface carrying fine sediment toward a sea you cannot see. The wind moves across the open land, and clouds drift slowly overhead. Every drop of water in that river has a story that began somewhere else on a distant slope or in a melting patch of ice. Its journey will continue through plains and basins until it becomes part of the global ocean that wraps around the world. Beneath the vast plains, winding rivers, and weathered mountain ranges of Rodinia, a quieter world was always in motion, hidden far below any horizon you could see. While the surface of the supercontinent appeared solid and unchanging, the layers beneath it were part of a slow, powerful system that never truly rested. Heat flowed upward from the planet's interior. Rock shifted under immense pressure, and the foundations of the land were constantly being reshaped by forces that worked on time scales far beyond ordinary experience. To begin understanding this hidden work, it helps to imagine Earth not as a single solid sphere, but as a layered structure, each layer with its own role in the planet's long story. At the center lies the core, a dense, hot region made mostly of iron and nickel. Surrounding it is the mantle, a thick shell of rock that, while solid in the everyday sense, behaves like a very slow-moving fluid over millions of years. On top of the mantle rests the crust, the thin outer skin that forms continents and ocean floors. The crust and the uppermost part of the mantle together make up the lithosphere, which is broken into large plates. These plates are not fixed in place. They float on the softer, warmer layer beneath called the asthenosphere and drift across the planet's surface. Their movement is driven by the transfer of heat from the deep interior to the cooler surface, a process that sets up slow circulating currents in the mantle. During Rodinia's time, these currents played a central role in both the assembly and the gradual destabilization of the supercontinent. Long before the land masses came together, mantle flow guided ancient continental fragments toward one another. As they collided, mountain ranges rose and thick roots of crust formed beneath them. The supercontinent became a patchwork of welded terrains, each carrying its own deep structural history. Yet, even as Rodinia stood united on the surface, the mantle below continued its restless motion. Heat built up beneath the thickened crust, especially in regions where old collision zones created zones of weakness. Over long periods, this heat began to soften and thin the lower parts of the lithosphere, making it more susceptible to stretching and cracking. This process did not happen all at once. It unfolded gradually, almost invisibly. Small fractures formed deep in the crust, far below the reach of surface erosion or weather. Magma generated by melting rock in the mantle began to rise into these fractures, cooling and solidifying as it went. Each intrusion added a thin layer of new material, subtly changing the composition and structure of the crust. In some regions, this activity concentrated along long linear zones. These were the early stages of rifts, areas where the land began to pull apart. At the surface, these zones might appear as broad, shallow valleys or elongated basins. Rivers were drawn toward these low points and sediments collected there, gradually filling the depressions. From below, however, the story was more dramatic. As the crust stretched, it thinned, allowing more heat to rise from the mantle. This increased melting, which in turn produced more magma, further weakening the crust and promoting additional stretching. Over time, this feedback loop could transform a stable region of continental crust into a zone of active separation. Elsewhere beneath Rodinia, different processes were at work along the margins of the supercontinent. Oceanic crust was often forced beneath continental crust in subduction zones. This occurred because oceanic crust is generally denser and thinner than continental crust. When the two met, the heavier oceanic plate tended to sink into the mantle. As it descended, it carried water and other materials down with it. These substances lowered the melting point of the surrounding rock, generating magma that rose back toward the surface. This magma fueled chains of volcanoes along the edges of the continent, adding new layers of rock to the land and releasing gases into the atmosphere. The sinking slabs of crust also played a role in driving mantle circulation. As cold, dense material descended, it displaced warmer, buoyant rock which rose elsewhere. This circulation helped maintain the overall flow of heat within the planet, linking surface processes to deep interior dynamics. Over millions of years, these subduction zones could consume entire ocean basins. What began as a wide stretch of open water between land masses gradually narrowed as the seafloor was pulled down into the mantle. Eventually, the remaining gap closed and the continents on either side collided, creating new mountain belts and thickening the crust. This cycle of opening and closing oceans, known as the Wilson cycle, is a fundamental pattern in Earth's tectonic behavior. Rodinia itself was the product of one such cycle formed from the closure of earlier oceans. Even as it existed, the seeds of the next cycle were already being sown in the mantle below. The deep structure of Rodinia's crust was far from uniform. Some regions were underlain by thick, stable cratons, ancient cores of continents that had resisted deformation for billions of years. These areas were relatively cool and rigid, making them less prone to rifting and tectonic disruption. Other regions, especially along old collision zones, were warmer and weaker. These zones often became the sites of renewed activity as heat and stress concentrated there. It was along these ancient seams that the supercontinent would eventually begin to split. The movement of heat from the mantle also influenced the elevation of the land. Hotter, less dense rock tends to rise, while cooler, denser rock sinks. Where mantle upwelling occurred beneath Rodinia, the surface above could be lifted, creating broad domes or highlands. Where cooler material descended, the surface might subside, forming basins. These vertical motions, though subtle on human time scales, had significant effects over millions of years. They influenced the direction of rivers, the location of coastlines, and the distribution of sediments. A region that slowly rose might become a source of erosion, while a region that sank could become a site of accumulation. Volcanism provided some of the most visible expressions of deep tectonic activity. In addition to the volcanic arcs along subduction zones, large-scale eruptions sometimes occurred within the interior of the supercontinent. These events were often associated with mantle plumes, columns of unusually hot rock rising from deep within the mantle. When a plume reached the base of the lithosphere, it spread out, heating and thinning the crust above. This could lead to widespread volcanic activity, producing vast flows of lava that covered large areas of the land. These lava fields, known as large igneous provinces, left thick layers of basalt that can still be found in ancient rock records. Such eruptions released enormous amounts of gas into the atmosphere, including carbon dioxide and sulfur compounds. These gases could influence climate on both short and long time scales, contributing to warming or cooling depending on their type and concentration. The interaction between tectonics and climate formed another feedback loop in the Rodian world. Mountain building increased weathering, which drew down carbon dioxide and promoted cooling. Volcanic activity added carbon dioxide, promoting warming. The balance between these processes helped guide the planet through cycles of climate change, including the deep freezes of snowball Earth and the warmer intervals in between. The magnetic field of Earth also connects to the deep interior, generated by the movement of molten metal in the outer core. This field extends far into space, protecting the planet from charged particles streaming from the sun. During Rodinia's time, the magnetic field was active, though it may have behaved somewhat differently than it does today. As tectonic plates moved, the rocks they carried recorded the direction and strength of the magnetic field at the time they formed. These records, preserved in the alignment of magnetic minerals, provide scientists with clues about the positions of continents in the distant past. In this way, the deep processes of the core and mantle indirectly help reveal the surface history of the supercontinent. Earthquakes were another surface expression of the hidden work below. Where plates ground past one another or where stress built up along faults, the sudden release of energy sent vibrations through the crust. These events would have been brief and localized, but over time they helped adjust the shape of the land, creating fractures and shifting blocks of rock. In the largely lifeless landscapes of Rodinia, the immediate impact of an earthquake might have been subtle. A cliff could collapse. A river channel might shift slightly. A new spring could open where groundwater found a fresh path to the surface. These small changes added to the ongoing reshaping of the land. The deep time perspective reveals how interconnected these processes were. The flow of the mantle influenced the movement of plates. Plate movement shaped mountains, rivers, and coastlines. These surface features affected climate and erosion. Erosion and sedimentation influenced the chemistry of the ocean and atmosphere. The atmosphere and ocean, in turn, affected the planet's temperature, which fed back into tectonic and volcanic activity. None of these systems operated in isolation. Each was part of a broader network, a planetary engine that transformed energy and matter across different layers of the Earth. It is also worth considering the scale of the forces involved. The pressure deep in the mantle is so great that rock behaves more like a slow-moving liquid than a solid. Temperatures reach thousands of degrees. The energy driving this system comes from a combination of residual heat from Earth's formation and the ongoing decay of radioactive elements within the planet. This energy has been powering tectonic activity for billions of years, and it continues to do so today. The continents we live on are still moving, still colliding, still pulling apart, guided by the same underlying processes that shaped Rodinia. During the later stages of Rodinia's existence, the balance between stability and change began to shift. The thick crust that had formed during the supercontinent's assembly acted as an insulating layer, trapping heat beneath it. Over time, this built-up heat made the interior of the supercontinent increasingly unstable. Rifting became more widespread. New fractures formed and old ones reactivated. Magma rose into these cracks and the crust thinned further. The land above began to sink in long, narrow zones, creating valleys that filled with water and sediment. These rift systems marked the first clear steps toward the breakup of the supercontinent. Although the surface still appeared unified, the deep structure was being reorganized. The mantle flow that once guided the continents together now began to guide them apart. The opening of new ocean basins is a slow process. At first, a rift valley forms on land. The stretching continues. The crust becomes so thin that magma can reach the surface and create new oceanic-type crust. Eventually, water floods in and a narrow sea forms. Over millions of years, this sea can widen into a full ocean, separating once connected land masses. Rodinia's future followed this path. The hidden work beneath its crust laid the groundwork for the continents we know today. Africa, North America, South America, Antarctica, and Australia all carry pieces of Rodinia's deep structure within them. Remnants of the time when they were part of a single whole. The evidence for this deep connection is found in matching rock types, similar mountain belt histories, and the alignment of ancient magnetic signals across widely separated continents. These clues allow scientists to reconstruct the slow dance of plates and mantle that unfolded over hundreds of millions of years. To reflect on this hidden world is to appreciate how much of Earth's story happens out of sight. The landscapes we see are only the surface expression of deeper ongoing processes. Every hill, valley, and coastline is shaped not just by wind and water, but by movements that begin far below in regions of heat and pressure we can never directly observe. As you continue listening, perhaps imagine the supercontinent from two perspectives at once. On the surface, rivers flow, microbial mats grow, and ice advances and retreats. Below, the mantle circulates, plates drift, and magma rises into cracks in the crust. Both views are part of the same reality, layered one above the other, connected through the slow transfer of heat, mass, and energy. The hidden work of the deep does not announce itself with constant drama. Instead, it shapes the world through persistence, guiding the planet from one configuration to the next, step by gradual step. Long before clocks divided time into neat, glowing numbers and calendars arranged days into orderly rows, the passage of light and darkness followed a simpler, deeper pattern, one set not by human design, but by the steady turning of the planet itself. On Rodinia's ancient surface, this turning shaped every sunrise and sunset, every shadow stretching across bare stone, and every subtle shift in temperature that followed the fatting of the sun. The rhythm of days and nights was not just a background feature of the world. It was a quiet force that influenced climate, atmosphere, oceans, and life in ways that unfolded over immense spans of time. Earth rotation is something we rarely think about even, though it defines the most basic cycle of our experience. The planet spins once on its axis, and in doing so it carries every point on its surface from light into darkness and back again. During the Proterozoic, when Rodinia existed, this rotation was slightly faster than it is today. A full day did not last 24 hours. It may have been closer to 22, or even a bit less depending on the exact point in time. This difference might seem small, but over millions of years, it added up to a significant change in the way energy moved through the Earth system. The slowing of Earth's rotation is driven largely by the gravitational interaction between the planet and the moon. Tides raised in the oceans by the moon's pull create friction, which gradually transfers energy from Earth's rotation to the moon's orbit, pushing the moon farther away and slowing the planet's spin. During Rodinia's time, the moon was closer to Earth than it is now, and its influence on the oceans and the planet's rotation was stronger. Tides were likely higher in many coastal regions, and the daily cycle of rising and falling water would have been more pronounced. This interaction between the spinning Earth and its satellite was part of a long, ongoing exchange of energy that continues to shape both bodies today. From the perspective of someone standing on Rodinia, the faster rotation would have meant that the sun moved across the sky a little more quickly. Dawn came sooner after night fell. Shadows shifted at a slightly faster pace. The window of daylight, though still long enough to feel complete, passed with a subtle urgency compared to the days we know now. This pace influenced how the land heated and cooled. During the day, sunlight warmed the surface of the supercontinent, causing the air above it to rise. At night, as the sun dipped below the horizon, the ground released that heat back into the atmosphere and then into space, allowing temperatures to drop. With shorter days and nights, these heating and cooling cycles happened more frequently. This had consequences for atmospheric circulation. Temperature differences between day and night help drive wind patterns, especially near the surface. Warmer air rises and is replaced by cooler air moving in from surrounding areas. On a world that spins faster, These daily pulses of warming and cooling interact with larger global wind systems in complex ways. The Coriolis effect, a result of Earth's rotation, also played a role. As the planet spins, moving air and water are deflected from straight paths, curving to the right in the northern hemisphere and to the left in the southern hemisphere. The strength of this deflection depends in part on the speed of rotation. A faster spinning Earth produces a stronger Coriolis effect, which can influence the structure of large-scale circulation patterns. During Rodinia's time, this may have led to differences in the size and shape of atmospheric cells that transported heat from equatorial regions toward the poles. The belts of rising and sinking air that govern where deserts, rain belts, and prevailing winds form could have been positioned differently or operated with different intensities than they do today. The oceans responded to this rhythm as well. Surface currents are driven by winds, and as winds follow curved paths due to Earth's rotation, the water they push follows similar patterns. The fastest spin of the planet may have influenced the way large looping currents moved around the edges of the supercontinent. These currents help distribute heat across the global ocean, carrying warm water away from sunlit regions and bringing cooler water back in return. The pace of this circulation, combined with the daily cycle of heating and cooling at the surface, contributed to the overall stability or variability of the climate. The boundary between day and night, known as the terminator, swept across Rodinia's surface in a steady, predictable motion. As it passed, the sky changed character. In the moments before sunrise, the horizon would brighten gradually, light scattering through the atmosphere and softening the darkness. After sunset, the last rays of the sun would linger, creating a slow fade into night. The quality of this light may have been influenced by the composition of the atmosphere, which included different amounts of gases and particles than it does now. Haze from volcanic emissions, dust from open landscapes, and chemical byproducts of early life could all have affected how sunlight scattered at dawn and dusk, giving these transitions their own distinct feel. Temperature shifts followed these changes in light. On bare rock and sediment without the insulating cover of forests or thick soils, the surface could heat up quickly under the sun and cool rapidly after nightfall. This created daily cycles of expansion and contraction in the rock itself. Over long periods, this repeated stress contributed to physical weathering, breaking stone apart and adding to the sediment that rivers carried across the land. For life, even at its simplest, the rhythm of light and darkness mattered. Photosynthetic microbes depended on sunlight to produce energy. During the day, they captured light and converted it into chemical forms that powered their growth and activity. At night, those processes slowed or stopped, and other metabolic pathways took over. This daily cycle created patterns in the chemistry of shallow waters and microbial mats. Oxygen levels could rise during daylight as photosynthesis released gas into the surrounding water and air, then fall at night as organisms consumed oxygen through respiration and chemical reactions, continued in the absence of light. In environments where oxygen was already scarce, these fluctuations could be significant, shaping which organisms could thrive in particular layers of a mat or in certain parts of a shallow sea. Some microbes adapted to tolerate changes in oxygen levels, while others specialized in conditions that were consistently low or high in oxygen. Early multicellular organisms, where they existed, would have been subject to these same cycles. Light availability influenced where they could live and how they grew. Some may have positioned themselves in ways that maximized exposure to sunlight or to the flow of nutrient-rich water during certain times of day. The night sky over Rodinia would have been a vast open display. With no artificial light and no tall vegetation to block the view, stars would have filled the darkness from horizon to horizon. The Milky Way would have appeared as a pale band stretching across the sky, its shape and position shifting slowly with the seasons as the planet orbited the sun. The moon, closer and appearing larger than it does now, would have had a strong presence in the night. Its light would reflect off the surface of the global ocean and the pale surfaces of ice and rock, creating long, bright paths across water and land. Lunar cycles added another layer to the rhythm of time. And as the moon moved through its phases, the amount of light it provided at night changed, and so did the strength of the tides. These changes influence coastal environments, affecting when shallow areas were flooded or exposed, and altering the conditions for microbial growth along the shore. The interaction between daily and monthly cycles created a complex pattern of variation. A coastal region might experience a particular combination of daylight, moonlight, and tidal height that repeated every few weeks. Over long periods, these repeating patterns could influence the structure of sediment layers and the distribution of life in these dynamic zones. Earth's tilt, which determines the seasons, also played a role. The angle of the planet's axis relative to its orbit around the sun causes different parts of the world to receive varying amounts of sunlight over the course of a year. This tilt existed during Rodinia's time, though its exact value may have varied slightly over geological periods. As a result, Rodinia experienced seasonal changes in temperature and light, especially in regions farther from the equator. Summers brought longer days and more intense sunlight. Winters brought shorter days and lower sun angles. These shifts influenced the growth and activity of microbial communities, the flow of rivers, and the formation and melting of ice in colder regions. Over even longer time scales, changes in Earth's orbit and tilt, known as Milankovitch cycles, altered the distribution of sunlight across the planet. These cycles, driven by gravitational interactions with other bodies in the solar system, affected the timing and intensity of seasons. They likely contributed to patterns of glaciation and warming during the Proterozoic, adding another layer of complexity to the climate system. The steady turning of the planet also influenced the deep interior in subtle ways. The rotation of the Earth contributes to the behavior of the liquid outer core, which generates the magnetic field. This field, in turn, shields the atmosphere from charged particles streaming from the sun, helping to prevent the gradual loss of gases into space. During Rodinia's time, this magnetic shield was active, though its strength and structure may have varied. Periodic reversals of the magnetic poles occurred, as they still do today, leaving records in the alignment of minerals in volcanic and sedimentary rocks. These records now help scientists track the movement of continents across the globe. From the perspective of daily experience, however, these deep processes were invisible. What mattered on the surface was the simple, reliable pattern of light and dark. The sun rose, the land warmed, winds shifted, shadows moved. The sun set, the land cooled, stars appeared. This predictability offered a kind of stability in a world where so much else changed slowly and quietly. Mountains rose and eroded, oceans circulated, the atmosphere evolved. Life experimented with new forms. Through all of it, the rotation of the planet provided a constant framework, a steady beat against which other processes played out. It is worth pausing to consider how this ancient rhythm connects to the one we experience now. Every day we live is part of the same long sequence of rotations that began when the Earth first formed. The length of the day has changed. The surface of the planet has transformed, and the life that experiences this cycle has become vastly more complex. But the underlying motion remains the same. Standing on Rodinia, watching the sun sink below a bare horizon, you would have been witnessing a moment in that unbroken chain. The light would fade, the air would cool, the sky would fill with stars. Somewhere far away on the opposite side of the planet, dawn would be breaking, beginning the cycle again. Far removed from the landscapes we can walk across and the skies we can look up into, the story of Rodinia survives only in fragments, scattered across the modern world like pieces of a puzzle that has been taken apart and mixed for hundreds of millions of years. There were no observers to record its shape, No maps drawn of its coastlines, no written accounts of its mountains, rivers, or frozen seas. Everything we know about this ancient supercontinent comes from careful interpretation. From reading subtle clues locked into stone, minerals, and the invisible signatures of forces that once acted on the planet. The work of reconstructing a lost world begins with a simple but powerful idea. Rocks remember, not in the way memory works in a living mind, but in the way their structure, composition, and internal patterns preserve information about the conditions under which they formed. Each layer of sediment, each crystal of mineral, each fold or fracture in the crust carries a record of pressure, temperature, chemistry, and motion. By learning how to interpret these records, scientists can trace the outlines of landscapes that no longer exist. One of the most important tools in this process is the study of ancient magnetism, a field known as paleomagnetism. Earth has a magnetic field generated by the movement of molten metal in its outer core. This field behaves roughly like that of a giant bar magnet with north and south poles that, while not fixed in place, provide a general direction at any given time. When certain types of rocks form, especially volcanic rocks and some sediments, tiny magnetic minerals within them align with the direction of the magnetic field. As the rock cools or hardens, these tiny alignments become locked in place. Millions or even billions of years later, scientists can measure the orientation of these minerals and determine the direction of the magnetic field at the time the rock formed. From this, they can infer the latitude at which the rock was located. A rock formed near the equator carries a different magnetic signature than one formed closer to the poles. By collecting paleomagnetic data from rocks of similar age on different continents, researchers can estimate how those continents were positioned relative to one another in the past. This method does not produce a single precise map, but it provides broad constraints helping to narrow down possible arrangements of land masses at different points in time. Another major line of evidence comes from the rocks themselves. Not just their magnetic properties, but their composition and structure. Mountain belts, for example, often form when continents collide. The rocks in these belts are deformed in characteristic ways, showing signs of intense pressure and heat. They may include specific types of metamorphic minerals that only form under certain conditions. When scientists find mountain belts of the same age and similar structure on continents that are now far apart, it suggests that those regions were once connected. The edges of the belts can be matched like the seams of a torn fabric, providing clues about how the land masses were once stitched together. These geological matches go beyond mountains. Layers of sedimentary rock can also serve as markers. A sequence of sandstones, shells, and limestones formed in a particular environment, such as a shallow sea or a river delta, can sometimes be traced across continents. If the same sequence appears in regions now separated by oceans, it hints that those areas once shared a continuous landscape. The chemistry of rocks adds another layer of information. Certain elements and isotopes are more abundant in some geological settings than in others. By analyzing the chemical signatures of rocks, scientists can infer where the material came from and what processes shaped it. For example, the presence of specific minerals might indicate that a rock formed in a volcanic arc, a deep ocean basin, or a continental interior. Fossils, though rare in rocks as old as those from Rodinia's time, provide additional context. When similar microossils or impressions of early multicellular life are found in sediments of the same age on different continents, it suggests that those environments were once connected or at least part of a similar ecological zone. While these biological clues are often subtle, they can help refine reconstructions of ancient geography. The age of rocks is another critical piece of the puzzle. Radiometric dating allows scientists to determine when a rock formed by measuring the decay of radioactive elements within it. Different isotopes decay at known rates, acting like natural clocks. By comparing the ratios of parent and daughter isotopes, researchers can calculate the time since the rock crystallized or the sediment was deposited. This dating helps establish timelines for geological events. If two regions on different continents show rocks of the same age that also share structural and chemical features, it strengthens the case that they were once part of the same system. Over time, these correlations build a framework for understanding the sequence of events that led to the assembly and breakup of supercontinents like Rodinia. Modern technology has expanded the range of tools available for this work. Satellite measurements provide detailed maps of Earth's gravity field, which can reveal variations in the density of the crust and mantle beneath the surface. These variations often correspond to ancient structures, such as buried mountain roots or old rift zones that are no longer visible at the surface. Seismic studies offer another window into the deep Earth. By analyzing how earthquake waves travel through the planet, scientists can infer the structure and composition of the crust and mantle. This helps identify thick, stable cratons and thinner, more deformed regions, providing clues about where ancient collisions and rifting events occurred. Computer models play a growing role as well. By combining geological, geophysical, and paleomagnetic data, researchers can test different configurations of ancient continents and see which ones best match the available evidence. These models allow scientists to explore how changes in continental arrangement might have affected climate, ocean circulation, and tectonic activity. The process of reconstruction is not straightforward. Data can be incomplete or ambiguous. Rocks can be altered by later events, obscuring their original signals. Magnetic records can be reset by heating or chemical changes. Sedimentary layers can be eroded or buried beneath younger deposits. Each piece of evidence must be carefully evaluated and placed in context. As a result, reconstructions of Rodinia have changed over time. Different models have been proposed, revised, and sometimes replaced as new data emerges. In some versions, certain continents sit closer together or farther apart. In others, the orientation of the supercontinent shifts. These differences reflect the ongoing nature of scientific inquiry, where understanding evolves as more information becomes available. One of the challenges lies in determining not just where the continents were, but how they were oriented. A continent can be rotated as well as moved, and paleomagnetic data alone cannot always distinguish between these possibilities. Geological features, such as the alignment of mountain belts or the distribution of sedimentary basins, help constrain these rotations. The reconstruction of ancient oceans is even more complex. Oceanic crust is constantly being created and destroyed through plate tectonics. Most of the ocean floor that existed during Rodinia's time has been recycled into the mantle and no longer exists. This means that scientists must infer the presence and size of ancient oceans, indirectly based on the arrangement of continents and the geological features along their margins. Despite these challenges, a broad picture has emerged. Rodinia is thought to have formed around 1 billion years ago, as earlier land masses collided and merged. It likely remained intact for several hundred million years before beginning to break apart, giving rise to new oceans and setting the stage for the formation of later supercontinents. The evidence for this cycle is found in the repeated patterns of mountain building, rifting, and sedimentation recorded in rocks around the world. Each cycle leaves behind a characteristic set of features that, when pieced together, reveal the rhythm of Earth's tectonic behavior over deep time. Another important source of information comes from the study of mineral grains within rocks. Some minerals, such as zircon, are particularly durable and can survive multiple cycles of erosion and deposition. Zircon crystals can be dated very precisely, and they often preserve information about the conditions under which they formed. By analyzing zircons from sedimentary rocks, scientists can trace the origins of the sediment back to specific source regions. If sediments in one area contain zircons that match the age and composition of rocks in a distant region, it suggests that those areas were once connected by a river system or part of the same land mass. This method allows researchers to map ancient drainage patterns and sediment pathways, adding another layer of detail to reconstructions of Rodinia's geography. It reveals not just where the continents were, but how water and material moved across them. The chemical composition of ancient seawater recorded in marine sediments also provides clues. Ratios of certain isotopes can indicate the temperature of the water, the amount of oxygen present, and the balance between volcanic input and weathering on land. These factors are influenced by the arrangement of continents and oceans. By comparing these chemical records with geological and paleomagnetic data, scientists can test whether a proposed configuration of Rodinia is consistent with known climate and ocean conditions. If a model predicts patterns that do not match the chemical evidence, it may need to be revised. This interplay between different lines of evidence is central to the scientific process. No single type of data tells the whole story. Instead, understanding emerges from the convergence of multiple independent sources of information. The reconstruction of Rodinia also benefits from studying younger supercontinents such as Pangea. Because Pangea existed more recently, its features are better preserved and easier to interpret. By understanding how Pangea formed and broke apart, scientists gain insight into the general processes that govern supercontinent cycles. These analogies help guide interpretations of older, more fragmentary evidence. They provide a framework for thinking about how continents behave over hundreds of millions of years, and how deep processes in the mantle influence surface geography. It is important to recognize that reconstructions are not exact replicas of the past. They are best estimates informed by the data available at the time. As new techniques are developed and new discoveries are made, these estimates can change. This openness to revision is a strength of science, not a weakness. It reflects a commitment to refining understanding rather than settling for a fixed narrative. The story of Rodinia is not a finished book, but an ongoing investigation with each new study adding another paragraph or correcting an earlier line. From a broader perspective, the effort to reconstruct a lost supercontinent highlights the deep connection between the present and the past. The mountains we see today may be the worn-down remnants of ancient ranges that once stood at the heart of Rodinia. The sediments beneath modern oceans may include grains of sand eroded from peaks that no longer exist. Even the distribution of certain mineral resources can reflect this ancient history. Or were deposits formed in specific tectonic settings during Rodinia's time, may now be scattered across different continents, carried along as the land masses drifted apart. The work of piecing together this history requires collaboration across many fields. Geologists, geophysicists, chemists, and computer scientists all contribute their expertise. Fieldwork in remote regions, laboratory analysis of tiny mineral grains, and large-scale modeling efforts all play a role in building the larger picture. There is also a sense of patience inherent in this work. Data collection can take years. Interpretations may take decades to settle into broad agreement. The time scales of the subject itself encourage a long view, one that values gradual progress over quick conclusions. To think about a world without witnesses is to reflect on the idea that most of Earth's history unfolded without any living thing capable of observing it in a human sense. The planet shaped itself through physical laws and chemical processes long before eyes or minds existed to take note. Yet, in a way, the rocks have become the witnesses. They carry the record forward, allowing beings that appeared much later to look back and reconstruct what happened. This connection across deep time is one of the quiet marvels of science. As you listen, perhaps imagine a scientist standing on a modern outcrop of ancient rock, running a hand across its rough surface. Beneath their fingers are minerals that formed in a world entirely unlike the one around them. The air, the climate, the arrangement of land and sea, and the forms of life are all different. Yet the same physical laws applied. The act of reconstruction is a bridge between those two worlds. It takes something solid and present, a piece of stone in the here and now, and uses it to reach back into a time that cannot be seen directly. In the ongoing story of Rodinia, this process of discovery continues to reveal new connections. Each matched mountain belt, each aligned magnetic signature, each dated mineral grain adds another point of reference, another anchor for understanding where the ancient land once lay. The picture that emerges is not a single static map, but a sequence of configurations showing how the supercontinent changed over time. It assembled, stabilized, and eventually began to break apart, leaving behind the scattered continents of the modern world. As you continue to rest with this idea, consider how much of your own surroundings might carry traces of that ancient past. The stones in a building, the sand beneath your feet, the minerals in everyday objects may all have origins that stretch back to times when Rodinia still existed as a single unified land mass. Subtle lines began to appear across the face of Rodinia, long before any ocean rushed in to claim new space, or any continent drifted far enough to feel truly separate. These lines were not visible as dramatic chasms or sudden breaks in the land. They started deep below the surface, in places where heat and pressure quietly weakened the planet's rigid shell. Over time, their presence worked its way upward, leaving gentle hints on the landscape that something within the unified world was beginning to change. The idea of a supercontinent pulling itself apart can feel almost like a contradiction. After all, Rodinia had been assembled through immense forces, collisions strong enough to raise vast mountain ranges and weld together ancient land masses into a single whole. Yet the same processes that created stability also carried within them the seeds of separation. The thickened crust that formed during those long collisions acted as an insulating layer, trapping heat beneath it. Over millions of years, that trapped heat altered the strength and behavior of the rock below, making some regions more flexible, more prone to stretching and more likely to fracture. To picture how this began, it helps to imagine the supercontinent as a broad, heavy blanket laid across a warm surface. The warmth below does not disappear. It builds. Eventually, the blanket starts to shift, wrinkle, and thin in places where the heat concentrates. In Rodinia's case, those places were often along old seams, the ancient collision zones where different continental blocks had been stitched together. These regions were structurally complex, filled with rocks that had already been bent, fractured, and altered by earlier events. As heat rose from the mantle, these weakened zones became natural pathways for change. The lower parts of the crust softened and slow stretching began. This stretching did not tear the land apart in an instant. Instead, it pulled the surface gently, almost imperceptibly, creating long, shallow depressions that could extend for hundreds or even thousands of km. At the surface, these early rifts might have looked like broad valleys rather than deep cracks. The land within them sat slightly lower than the surrounding terrain, drawing in water and sediment from nearby areas. Rivers adjusted their courses, flowing into these low points. Lakes and shallow basins formed, filling the elongated depressions with water that reflected the sky above. These rift valleys became collectors of the landscape's history. Sediment washed down from surrounding highlands settled into their floors layer by layer. Over time, thick sequences of sand, mud, and gravel built up, recording changes in climate, erosion, and water flow. In some regions, volcanic activity accompanied this process, adding layers of lava and ash to the growing stacks of sediment. From below, the story was more dynamic. As the crust stretched, it became thinner, allowing more heat to rise from the mantle. This heat caused parts of the lower crust and upper mantle to melt, generating magma. The magma moved upward through fractures and weaknesses, sometimes solidifying underground as intrusions, and sometimes reaching the surface in volcanic eruptions. These eruptions did not always form tall, cone-shaped volcanoes like the ones we often imagine. In many cases, magma flowed out through long cracks, spreading across the land in wide, flat sheets. These lava flows cooled and hardened into layers of basalt, creating broad plateaus of dark, dense rock. Each new layer added weight to the crust, which could cause further sinking in the rift zones. This sinking, in turn, made more space for sediment and water to accumulate. The process fed back on itself, gradually deepening and widening the rift valleys. As these features grew, they began to influence the climate and ecosystems of the surrounding regions. The low-lying basins could trap moisture, creating localized environments that were wetter than the surrounding highlands. This supported the growth of microbial communities in shallow waters and along the margins of lakes and rivers. The presence of standing water also altered the chemistry of these regions. Minerals dissolved into the water and chemical reactions took place that differed from those in flowing rivers or the open ocean. These unique conditions left their own signatures in the sediments, which scientists now use to identify ancient rift environments in the rock record. Not all rifts followed the same path. Some stalled and eventually faded, filled in by sediment and erased by later erosion. Others continued to stretch and deepen, becoming long-lived features that shaped the future of the planet. In places where stretching persisted, the crust eventually became so thin that it could no longer support the weight of the land above. It fractured more completely, allowing magma to rise continuously and form new crust that resembled the ocean floor rather than continental land. At this stage, water from the surrounding ocean began to seep into the rift. What started as a valley on land slowly transformed into a narrow sea. Over time, as the plates on either side continued to move apart, this sea widened, deepened, and developed the full characteristics of an ocean basin. The transformation from rift valley to ocean did not happen quickly. It took millions of years for the process to reach that point. During much of this time, the supercontinent still appeared largely intact, even as deep changes were underway. The emergence of these new seas marked a turning point in Rodinia's history. Where there had once been continuous land, there were now growing gaps filled with water. The global ocean, which had once wrapped around the outside of the supercontinent, began to push inward, claiming new territory. This shift affected ocean circulation. New pathways opened for currents to move between different regions of the sea. Heat distribution patterns changed, influencing climate on a global scale. Coastal environments expanded as new shorelines formed along the edges of the developing basins. The atmosphere responded as well. Increased volcanic activity associated with rifting released gases into the air, including carbon dioxide and sulfur compounds. These emissions could influence temperature and cloud formation, contributing to regional and global climate changes. At the same time, the creation of new coastlines and shallow seas provided fresh habitats for life. Microbial mats spread across newly formed shelves. Nutrients delivered by rivers and upwelling currents supported bursts of biological activity in these expanding coastal zones. From a surface perspective, the changes might have felt gradual and unremarkable. A valley slowly widened. A lake grew deeper. A shoreline shifted slightly inland or outward. Yet over geological time, these small adjustments added up to a fundamental reorganization of the planet's surface. The direction in which Rodinia began to break apart was not uniform. Different regions experienced rifting at different times. Some parts of the supercontinent remained stable long after others had begun to separate. This uneven process created a complex pattern of emerging land masses and seas. Ancient continental blocks that had once been neighbors started to drift away from each other. Their shared mountain belts were split. Rivers that once flowed across continuous land found their paths cut by new basins. Sediments that would have been carried to a distant shore instead settled into newly formed seas. The movement of plates during this period was guided by the same mantle currents that had once drawn them together. These currents did not change direction overnight. They evolved, responding to shifts in heat distribution and the changing configuration of the lithosphere. As the supercontinent began to fragment, the flow of the mantle adjusted. Rising plumes of hot rock found new routes to the surface beneath thinning crust. Sinking slabs of cooler, denser material descended into the mantle along newly formed subduction zones at the edges of emerging plates. This reorganization of deep processes reinforced the surface changes. Rifting became more focused in some areas, while other regions experienced increased compression and mountain building as plates adjusted to their new paths. The breakup of a supercontinent is not a simple act of pulling apart. It is a rebalancing of forces across the entire planet. Every change in one region influences conditions elsewhere through shifts in stress, heat flow, and circulation. The formation of new oceans also altered the chemical exchanges between land, sea, and atmosphere. Fresh seafloor created by volcanic activity reacted with seawater, influencing the composition of the ocean. New sedimentary basins trapped carbon and nutrients, affecting the long-term cycles that regulate climate. These changes had implications for life as well. Expanding coastlines increased the area of shallow, sunlit waters, which were among the most productive environments for early life. This may have provided new opportunities for biological diversification and the spread of more complex organisms. The shifting arrangement of land and sea also influenced migration pathways for life. Even at the microbial level, currents carried organisms and nutrients between newly connected regions of the ocean. Rivers delivered materials to different coastal zones. As drainage patterns changed, the sense of a single unified world began to fade. As these processes continued, the supercontinent's interior, once far from any ocean, moved closer to new shores. Regions that had shared the same climate and ecosystems found themselves in different settings as plates drifted apart. It is important to remember that this transformation did not have a clear beginning or end. There was no single moment when Rodinia could be said to have broken. Instead, there was a long period of transition during which the supercontinent existed in a state that was neither fully whole nor fully divided. During this time, the landscape would have been a mix of old and new. Ancient mountain belts stood alongside fresh volcanic plateaus. Long-established river systems were rerouted by developing basins. New coastlines formed even as others remained unchanged. The record of these changes is preserved in rocks that show a progression from continental sediments to volcanic layers to marine deposits. These sequences tell a story of land giving way to sea, of valleys becoming straits, and of narrow seas growing into wide oceans. In some regions, the evidence appears as thick piles of basalt overlain by layers of shallow marine sediment. In others, it shows up as faulted blocks of crust tilted and buried beneath younger deposits. Each location offers a different perspective on the same broad process. The fragmentation of Rodinia also influenced the planet's magnetic record. As new crust formed and plates moved, the alignment of magnetic minerals in rocks changed. These changes now provide a timeline of movement, helping scientists trace the paths of continents as they drifted away from their ancient neighbors. The human mind often looks for clear divisions, for moments when one state ends and another begins. The breakup of a supercontinent does not fit neatly into that way of thinking. It is a story of overlap, of gradual transitions and long periods of coexistence between old structures and new ones. To imagine standing on Rodinia during this phase is to picture a land that feels both familiar and subtly unsettled. The ground beneath your feet still stretches far in every direction, but in some places you might notice a wide valley filled with water that was not there before. In the distance, dark bands of volcanic rock mark where the Earth's interior has reached the surface. Rivers flow into basins that seem to deepen with time. The air carries faint traces of volcanic gases. The horizon includes new shorelines where waves meet land that was once far from any sea. These are the first signs of a world in transition, hints that the long unity of the supercontinent is giving way to a more divided future. Yet for millions of years, the change remains incomplete, the process ongoing. Over immense stretches of time, the shape of the world began to change in ways that would eventually make the single unified land of Rodinia feel like a distant memory, rather than a present reality. What had once been a continuous expanse of connected terrain slowly transformed into a collection of drifting pieces, each carrying with it fragments of a shared past and the seeds of a very different future. This transformation did not happen with sharp edges or sudden breaks. It unfolded through gradual motion, guided by the deep currents of the mantle and the steady pull of tectonic forces that reshaped the planet one subtle adjustment at a time. As rift valleys widened and narrow seas formed within the body of the supercontinent, the sense of a single uninterrupted world began to soften. Water flowed into these growing basins, creating long, shallow straits that cut through land that had once been continuous. The edges of these new waterways became fresh coastlines, places where waves met rock for the first time in millions of years. Along these margins, erosion began its familiar work, carving cliffs, forming beaches, and spreading sediment across newly formed shelves. Beneath the surface, the separation was driven by changes in the way heat moved through the planet. The thick crust of Rodinia, built up during its long assembly, had trapped warmth from below. Over time, this heat weakened the lower parts of the lithosphere, allowing it to stretch and thin in certain regions. Where thinning became extreme, the crust fractured completely, and magma rose to the surface, creating new rock that resembled the ocean floor rather than continental land. Once this process reached a critical point, a new phase of movement began. Instead of simply stretching, the two sides of a rift started to move apart more clearly. The narrow seas that had formed widened into true ocean basins, and the plates carrying the fragments of Rodinia began their long journeys across the globe. Each fragment moved at its own pace and in its own direction, guided by the flow of the mantle beneath. Some drifted toward the equator, entering warmer climates. Others moved toward higher latitudes, encountering cooler conditions. These changes in position influenced their future landscapes, climates, and ecosystems in ways that would unfold over hundreds of millions of years. The first major divisions created a set of large continental blocks that would later become the cause of modern continents. Pieces that now form parts of North America, South America, Africa, Antarctica, Australia, and Eurasia began to separate from one another, though not all at once and not in the same way. The paths they followed were shaped by the geometry of the rifts and the forces acting at their edges. In some regions, new oceanic crust formed steadily, pushing the land masses farther apart. In others, movement slowed or changed direction, as plates interacted with neighboring regions or encountered zones of subduction. The global ocean, which had once wrapped around Rodinia from the outside, now began to flow through the gaps within it. New currents formed, linking previously isolated parts of the sea. This reorganization of ocean circulation altered the distribution of heat and nutrients, influencing climate patterns and the productivity of marine environments. Coastlines multiplied as land broke into separate pieces where no's had once been long, continuous shores. New inlets, bays, and shallow seas appeared. These areas became centers of geological and biological activity. Sediments accumulated rapidly in the new basins, recording the early stages of each continent's independent history. The land itself responded to this separation, with changes in elevation and structure. Some regions rose as the crust adjusted to the loss of neighboring support. Others sank, forming broad continental shelves or deepening basins. Rivers found new routes to the sea, sometimes cutting through young coastal ranges or flowing into newly formed gulfs. The breakup also influenced volcanic activity. As plates moved apart, magma continued to rise along the spreading centers, creating long chains of volcanic ridges on the seafloor. These ridges marked the boundaries between diverging plates and served as sites where new oceanic crust was constantly being created. Along the edges of the drifting continents, different processes took hold. In some places, oceanic crust began to sink beneath continental margins, forming subduction zones. These zones generated volcanic arcs and mountain belts, adding new layers of complexity to the growing continents. This combination of spreading at some boundaries and collision at others meant that the breakup of Rodinia was not simply a matter of land drifting away into open space. It was a dynamic reorganization of the entire plate system, with new interactions forming even as old ones faded. As the fragments moved, they carried with them the geological memory of their time as part of a single landmass. Ancient mountain belts, once continuous across Rodinia, were split and distributed across different continents. Today, geologists can trace these belts from one land mass to another, finding matching rock types and structures that reveal their shared origin. For example, parts of eastern North America share deep geological similarities with regions in northwestern Africa and Western Europe. These connections are remnants of ancient collisions and separations that began with the breakup of Rodinia and continued through later supercontinent cycles. The movement of continents also influenced the atmosphere and the long-term climate of the planet. As land masses spread out, weathering processes became more widespread and more evenly distributed. Rivers delivered minerals to multiple ocean basins rather than to a single global sea. This altered the balance of carbon dioxide between the air, the land, and the ocean, contributing to shifts in temperature over geological time. The expansion of shallow seas along the margins of the new continents created broad areas where sunlight, nutrients, and water came together. These environments were particularly favorable for life, supporting extensive microbial communities and later, more complex organisms. The increase in coastline length compared to the time of Rodinia meant that productive marine habitats became more common. The separation of land masses also created barriers and pathways for the movement of life. Even at the microbial level, changes in ocean circulation and water chemistry could influence which organisms thrived in different regions. Over time, these differences contributed to the diversification of life as populations adapted to their local conditions. On land, the creation of new mountain belts and basins altered wind patterns and rainfall distribution. Some regions became wetter as they moved into the path of prevailing winds and ocean currents. Others became drier as they drifted into rain shadows or away from sources of moisture. These changes in climate and landscape set the stage for the later development of more complex ecosystems, including the eventual spread of plants and animals across the continents. The groundwork for that future was laid during the slow separation of Rodinia, even though the living world at the time remained mostly simple and small. The story of this transformation is preserved in the rocks that formed during and after the breakup. Thick sequences of volcanic basalt mark the early stages of seafloor spreading. Layers of marine sediment record the flooding of rift valleys and the growth of new oceans. Faulted and tilted blocks of crust reveal the stretching and bending that accompanied separation. By studying these records, scientists can trace the paths of the continents as they moved away from one another. Paleomagnetic data shows how their positions changed over time. Radiometric dating provides timelines for when key events occurred. Together, these tools allow researchers to reconstruct a series of maps showing the gradual transition from one land mass to many. It is important to remember that the breakup of Rodinia was not the end of the supercontinent cycle. The fragments that emerged did not remain separate forever. Over hundreds of millions of years, they would continue to move, sometimes colliding again to form new supercontinents such as Pangea and later Pangea. In this way, Rodinia can be seen as one chapter in a much longer pattern of assembly and dispersal. The planet has gone through multiple cycles of continents coming together and pulling apart, each cycle reshaping the surface and influencing the course of life and climate. The legacy of Rodinia is woven into the structure of the modern world. The distribution of ancient cratons, the alignment of mountain belts, and the location of certain mineral resources all reflect the supercontinent's former configuration. Even the shape of today's oceans and continents carries traces of this ancient past. The Atlantic Ocean, for example, occupies a space that has been opened and closed multiple times through successive supercontinent cycles. Its current form is the latest in a series of transformations that began long before Rodinia existed. From a broader perspective, the breakup of Rodinia highlights the deep interconnectedness of Earth's systems. Changes in the deep mantle influenced the movement of plates. Plate movement reshaped land and sea. These changes affected climate, ocean circulation, and the distribution of life. In turn, biological and chemical processes influence the atmosphere and the long-term balance of heat within the planet. This web of interactions means that the story of Rodinia's transformation is not just a geological tale. It is a planetary one, involving every layer of the Earth from the core to the atmosphere. To imagine this period is to picture a world in motion, even if that motion was almost imperceptible on any single day. The coastline you might stand on one morning would still be there the next, and for countless generations. Yet over millions of years, that same coastline would shift, move, and perhaps vanish entirely as the land it belonged to drifted away. The sense of scale can be difficult to hold in mind. Human history spans a few thousand years. The separation of Rodinia unfolded over hundreds of millions. The processes at work moved at a pace that makes the idea of change feel almost abstract. Yet their effects were anything but small. As the fragments of the supercontinent moved farther apart, the distances between them grew. New oceans widened. Currents established long looping paths across the globe. Climate patterns adjusted to the new arrangement of land and water. These changes created the conditions for the next great phases of Earth's history. The spread of shallow seas and the stabilization of oxygen levels in the atmosphere set the stage for the rise of more complex life forms in the eras that followed. The reshaped continents provided new habitats and new challenges, driving evolutionary innovation. In this sense, the breakup of Rodinia was not just an ending. It was a beginning, a transition from a world dominated by a single unified land mass to one characterized by diversity in geography, climate, and life. Standing in imagination at the edge of one of these newly formed seas, you might watch waves roll in against rock that had only recently been part of a vast interior. The air would carry the scent of salt for the first time in that place. The horizon would open up in a new way, no longer bounded by continuous land, but by water stretching outward toward another drifting piece of the world. Rivers that once flowed toward a distant outer ocean now found a nearer destination. Sediments that would have traveled thousands of kilometers to reach the sea settled instead in these young basins. The landscape adjusted, finding new balances between erosion and deposition, between uplift and sinking. The continents themselves became travelers. Carried by the slow motion of the plates, they crossed latitudes, experienced different climates, and encountered new neighbors. Their journeys would lead to collisions that raise new mountains and to separations that open new oceans, repeating the cycle that had first brought Rodinia together. Here in the quiet space of the present moment, it becomes possible to hold two worlds in mind at once. One is the one you are in right now with its familiar skis, its scattered continents, its long coastlines, and the steady hum of modern life. The other is a world that no longer exists. A planet shaped into a single immense land mass, surrounded by a global ocean and guided by rhythms so slow and vast that they stretch far beyond everyday experience. Rodinia belongs to that second world. Yet traces of it still linger in the ground beneath your feet and in the shape of the Earth itself. To stand in the present and listen for an ancient planet is not about hearing a literal sound. It is about noticing the quiet connections that run through time, linking what is now to what once was. The stones in a path, the sand on a beach, the layers of rock in a distant cliff, all carry within them fragments of a story that began long before any human presence. Some of those fragments may have been part of mountains that rose when Rodinia was still whole. Others may have settled at the bottom of seas that formed as the supercontinent began to break apart. The sense of distance between then and now can feel almost overwhelming. Rodinia existed hundreds of millions of years before the first animals walked on land, before trees rooted themselves in soil, before even the most familiar shapes of life took form. Yet, despite that distance, the processes that shaped that ancient world are still at work today. Plates continue to move. Mountains continue to rise and erode. Oceans continue to open and close. The same engine that guided the assembly and separation of Rodinia still turns beneath the surface of the planet. It can be grounding to realize that the Earth you live on is not a finished product. It is part of an ongoing process, one that began long before you arrived and will continue long after. The continents you recognize on a map are not permanent fixtures. They are temporary arrangements in a cycle that has repeated itself multiple times across deep history. When you look at a modern coastline, for example, you're seeing a boundary that will one day change. Sea levels will rise and fall. Land will lift or sink. What is shoreline now may become inland terrain, and what is land now may one day lie beneath water. In Rodinia's time, many places that are now far from any ocean were once near the sea. And many places that now lie beneath waves were once part of a vast interior. This shifting perspective can make the present moment feel both smaller and larger at the same time. Smaller because human time scales are so brief compared to the spans of geological change. Larger because you are part of a much longer story, one that connects your moment to events that took place hundreds of millions of years ago. Consider the idea that some of the atoms in your body may have been part of that ancient world. Water molecules cycle through oceans, clouds, rivers, and living things. Carbon moves between air, rock, and life. The materials that once passed through Rodinia's rivers and seas are now part of the global system that supports the world you inhabit. The air you breathe is shaped by processes that began long before complex life existed. Oxygen levels in the atmosphere rose and fell over time, influenced by the activity of early microbes, the burial of organic matter, and the movement of continents. The balance that allows animals and humans to breathe comfortably is the result of countless interactions between land, sea, air, and life over deep time. Even the shape of the sky you see at night carries echoes of that ancient past. The stars themselves are far older than Rodinia, but the way you see them from Earth is influenced by the planet's rotation, its tilt, and its orbit. All of which have been shaped by the same gravitational interactions that govern the world when the supercontinent still existed. When you imagine standing on Rodinia, you might picture a wide, open landscape under a vast sky with no familiar signs of modern life. Yet the sky above would have held the same constellations, the same distant galaxies, and the same slow movement of celestial bodies. The connection between Earth and the larger universe has always been there, even as the surface of the planet transformed again and again. Listening to a world that no longer exists can also mean paying attention to the subtle ways the past influences the present. The distribution of mountains, for instance, is not random. Many modern ranges trace their origins back to ancient collisions that occurred when supercontinents assembled. The worn-down roots of those old mountains still shape landscapes, influence weather patterns, and guide the flow of rivers. The availability of certain minerals and resources also reflects this deep history. Deposits of metals, coal, and other materials often form in specific tectonic or environmental settings. The fact that these resources are found in particular places today is tied to the configuration of continents and oceans long ago. Even the broad patterns of climate are influenced by the arrangement of land and sea. The presence of continents in certain positions affects ocean currents, which in turn distribute heat around the globe. The climate you experience is in part the result of a long chain of events that includes the assembly and breakup of ancient supercontinents like Rodinia. There is a quiet continuity in all of this. The planet changes, but it does so through processes that remain consistent in their nature. Heat flows from the interior to the surface. Gravity pulls water downhill and shapes coastlines. The sun provides energy that drives winds, currents, and life itself. These forces were present during Rodinia's time, and they are present now. What changes is the arrangement of the pieces. The land shifts, the seas move, the living world adapts, the story evolves, but the underlying rules remain. In the present, it is easy to think of the world as fixed, as something that simply is the way it is. Roads, cities, and borders reinforce that feeling of permanence. Yet, when you step back into the perspective of deep time, that sense of stability begins to soften. Everything you see becomes part of a temporary pattern, one moment in a long sequence of configurations. This does not make the present less meaningful. If anything, it can make it feel more valuable. Your moment exists within a vast continuum, and it is unique within that flow. The world you experience has never existed in quite the same way before, and it will not exist in exactly the same way again. Rodinia's world, for all its differences, was once just as real to the simple life that inhabited it as your world is to you. The microbial communities that spread across shallow seas and riverbeds existed within their own present, shaped by the conditions of their time. They did not know they were part of a story that would be reconstructed hundreds of millions of years later by beings capable of looking back across deep time. There is something quietly profound in that idea. The past does not know it is the past. It simply unfolds as the present for those who live within it. In the same way, the present you experience now will one day be part of a history that others look back on. Even if the world has changed in ways that are hard to imagine, standing in this awareness can bring a sense of calm. The pressures and urgencies of daily life can feel intense, but they exist within a much larger frame. The planet has moved through states of deep cold and deep warmth, through unity and separation, through simplicity and complexity. It will continue to move through changes long after individual moments have passed. This does not mean that what happens now does not matter. The choices made by humans affect the world in ways that can resonate far into the future. The atmosphere, the oceans, and the living systems of the planet respond to actions taken on relatively short time scales. In that sense, the present moment carries weight within the long story of Earth. Yet there is also comfort in knowing that the planet itself is resilient in a deep structural way. It has adapted to dramatic changes before. It has found new balances after periods of extreme disruption. The story of Rodinia, with its cycles of assembly, freezing, separation, and renewal, is one example of that broader pattern. As you rest with this idea, you might imagine the surface of the Earth as a kind of slow-moving tapestry. Threads of rock, water, air, and life are woven together, pulled apart, and woven again in different patterns. Each pattern lasts for a time, then gives way to another. The present pattern includes continents scattered across the globe, oceans that connect them, and a living world rich with complexity. The pattern that included Rodinia was different, yet it was woven from the same threads. Listening to a world that no longer exists can also be an invitation to pay closer attention to the one that does. The sound of wind, the movement of water, the texture of stone, and the rhythm of light and dark are all part of the same set of processes that shaped the ancient past. When you notice these things, you are in a small way tuning into the same forces that operated on Rodinia. The wind that moves through trees today is driven by the same physics as the wind that swept across bare rock in the Proterozoic. The waves that break on a modern shore follow the same gravitational rules as the waves that rolled against Rodinia's long, empty coastlines. There's a sense of continuity in that, a reminder that the planet's story is not made of isolated chapters, but of a single flowing narrative. In the quiet of this moment, you might picture the Earth turning slowly in space. One side in sunlight, the other in darkness. That turning has never stopped. It continued through the time of Rodinia, through the rise of more complex life, through the formation of later supercontinents, and into the world you inhabit now. The land beneath you, whatever form it takes, is riding along on that motion, carried by a planet that is both ancient and alive in its own way. If you let your thoughts drift back to the beginning of this journey, you might recall the image of a single unified world, all lands gathered together. From that starting point, the story moved through climate, water, deep forces, separation, and transformation. Now it arrives here in a present shaped by all of those past events. The fact that you can think about Rodinia at all is itself a result of the long chain of changes that followed its breakup. The spread of shallow seas, the stabilization of oxygen levels, and the rise of more complex life eventually led to a world where beings could ask questions about their planet's deep history. In that sense, Rodinia's legacy is not just written in rocks. It is also present in the curiosity that drives people to study those rocks, to piece together the outlines of a world that vanished long before memory or record. As you continue on with whatever comes next after this moment, you carry that connection with you, whether you think about it or not. The ground beneath your feet, the air around you, and the water that flows across the surface of the planet are all part of a system that has been evolving for billions of years. The world that no longer exists is not truly gone. It is folded into the one that does. And so rather than closing a door on Rodinia, it can feel more fitting to think of this as stepping back into the present with a slightly wider view. The ancient supercontinent becomes one layer in a much deeper stack of time, one configuration among many in the long history of a changing planet. In the gentle quiet of this thought, you might take a slow breath and notice where you are. The room, the light, the sounds around you are all part of a world shaped by forces that reach far back into deep time. The story of Rodinia does not end here. It continues in the continents that drift today, in the oceans that circulate, and in the life that adapts to changing conditions. It continues in the questions that people ask about the past, and in the ways those questions shape how the present is understood. If you find yourself looking at a map, a stone, or a stretch of coastline in the future, you might remember that there was once a time when all of that was part of a single vast land. The memory of that unity, preserved in the planet itself, is still there, waiting quietly beneath the surface. For now, you can let that image settle gently into the background of your thoughts. The Earth turns. The day moves into night, or night into day, depending on where you are. The present moment flows forward, carrying with it the echoes of a world that no longer exists, yet still, in so many ways, remains.